Relativity, the illusion of now. What time is it right now? Look at your watch, check your phone. You probably think you know the answer. But here's the mind-blowing truth. There is no universal now. Time isn't the constant, unchanging river we imagine it to be. It's flexible, malleable, and deeply weird. Einstein showed us that time is relative. It flows at different rates depending on how fast you're moving and how strong the gravitational field is around you. This isn't just theoretical physics mumbo-jumbo. It's measurable, testable, and absolutely real. And it changes everything we thought we knew about the universe. Welcome to the strangest chapter in our cosmic story, the chapter where we discover that time itself is an illusion. Your head is aging faster than your feet. Let's start with something truly bizarre. Right now, as you read this, your head is aging faster than your feet, not by much. We're talking billionths of a second over a lifetime, but it's measurable and real. Why? Because of gravitational time dilation. Einstein's general relativity tells us that time moves slower in stronger gravitational fields. Your feet are slightly closer to Earth's center than your head, so they experience slightly stronger gravity. This means time passes slightly slower for your feet than for your head. Scientists have measured this effect using atomic clocks, the most precise timekeeping devices ever created. In 2010, researchers at the National Institute of Standards and Technology placed two atomic clocks at different heights, one just 33 centimeters, about 1 foot, higher than the other. The higher clock ran faster, ticking ahead by about 90 billionths of a second per day. Think about that. Just by raising a clock 1 foot, time speeds up. If you live in a penthouse apartment, you're aging faster than someone in a basement. Mountain climbers age faster than deep-sea divers. Astronauts on the International Space Station, orbiting 400 kilometers above Earth, age slightly faster than people on the ground. This isn't science fiction. This is reality. Time is not universal. It's personal, local, and depends on where you are in a gravitational field. GPS satellites prove Einstein every day. If you've ever used GPS to navigate, you've relied on Einstein's theory of relativity. GPS satellites orbit Earth at about 20,000 kilometers altitude, where gravity is weaker than on the surface. According to general relativity, their clocks should run faster than clocks on Earth, about 45 microseconds per day faster. But there's a twist. The satellites are also moving at about 14,000 kilometers per hour relative to Earth's surface. According to special relativity, moving clocks run slower. This effect causes the satellite clocks to lose about 7 microseconds per day. The net effect? GPS satellite clocks gain about 38 microseconds per day compared to Earth clocks. That might not sound like much, but light travels 30 centimeters in a nanosecond. In 38 microseconds, light travels 11.4 kilometers. Without correcting for relativity, GPS would accumulate errors of over 10 kilometers per day. Engineers programmed GPS satellites to account for these relativistic effects. Every time you use GPS, you're proving Einstein right. Relativity isn't just theory, it's the reason you can find the nearest coffee shop. Time travel to the future is real. Here's something that will blow your mind. Time travel to the future is not only possible, it's been done. Many times, by humans. Russian cosmonaut Sergei Krikalev holds the record for time travel. He spent 803 days in space, orbiting Earth at high speeds. Because of time dilation, he aged about 0.02 seconds less than he would have on Earth. He traveled 0.02 seconds into the future. That might not seem impressive, but it proves the principle. If we could build a spacecraft that travels at 99.9% the speed of light, time dilation becomes dramatic. 1 year on that spacecraft would equal about 22 years on Earth. Travel for 10 years at that speed, return home, and 220 years would have passed on Earth. You'd have traveled 210 years into the future. This isn't speculation. It's physics. The only limitation is engineering. We don't yet have the technology to accelerate spacecraft to such extreme speeds, but the physics is solid. Time travel to the future is real and achievable. The twin paradox isn't a paradox. One of the most famous thought experiments in relativity is the twin paradox. Imagine identical twins. One stays on Earth, the other boards a spacecraft, travels to a distant star at near light speed, and returns. When they reunite, the traveling twin is younger. This seems paradoxical because, from the traveling twin's perspective, Earth was moving away and then returning. Shouldn't the Earth twin be younger? The resolution is that the situation isn't symmetric. The traveling twin accelerates, decelerates, turns around, and accelerates again. The Earth twin doesn't. Acceleration breaks the symmetry. The traveling twin really does age less. This has been tested with atomic clocks on airplanes. In 1971, physicist Joseph Heffel and astronomer Richard Keating flew atomic clocks around the world on commercial airliners. When they compared them to clocks that stayed on the ground, the flying clocks had aged less by exactly the amount predicted by relativity. The twin paradox isn't a paradox, it's reality. If you want to stay young, keep moving fast. Agujeros, black holes, where time stops. Near a black hole, time dilation becomes extreme. As you approach the event horizon, the point of no return, time slows down dramatically from an outside observer's perspective. Imagine watching someone fall into a black hole. As they approach the event horizon, they appear to slow down. Their movements become sluggish. Light from them becomes redshifted, dimmer. They appear to freeze at the horizon, never quite crossing it, fading from view as the light becomes too redshifted to see. But from the falling person's perspective, nothing special happens at the horizon. They cross it in finite time, experiencing no slowdown. They continue falling toward the singularity at the center. This creates a bizarre situation. From outside, the person never crosses the horizon. From inside, they cross it and continue falling. Both perspectives are correct. Time is relative. At the event horizon of a black hole, time dilation becomes infinite. Time, as measured by a distant observer, stops. This is why black holes are sometimes called frozen stars. From our perspective, matter falling into them appears frozen in time at the horizon. You can't travel. Back in time. Probably. Time travel to the future is easy. Just move fast or hang out near a massive object. But what about traveling to the past? Can you go back and prevent your own birth, creating a grandfather paradox? The short answer is, probably not. While general relativity allows for solutions that include closed time-like curves, paths through space-time that loop back on themselves, these solutions require exotic conditions that probably don't exist in our universe. One proposed method is the wormhole, a tunnel through space-time connecting two distant points. If you could create a wormhole and manipulate it correctly, you might be able to travel back in time. But wormholes require negative energy density, something we've never observed, and which may be impossible. Another proposal is the Tipler cylinder, an infinitely long, rapidly rotating cylinder of matter. Fly around it in the right way, and you could travel back in time. But infinitely long is a problem. We don't have infinite amounts of matter. Most physicists believe there's a chronology protection conjecture, a law of physics we haven't discovered yet that prevents time travel to the past. Stephen Hawking famously said, "The best evidence we have that time travel is not possible and never will be is that we have not been invaded by hordes of tourists from the future." Time began at the Big Bang. Here's a mind-bending fact. Time itself began at the Big Bang. There was no before the Big Bang, because time didn't exist yet. This is hard to wrap your head around. We're used to thinking of time as eternal, stretching infinitely into the past and future. But according to general relativity, time is part of space-time, and space-time began at the Big Bang. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because before requires time, and time didn't exist. Some theories propose that our universe is part of a larger multiverse, where time might exist in some broader sense. Others suggest the universe is cyclical, with big bangs and big crunches repeating eternally. But within our universe, Time had a beginning 13.8 billion years ago. The arrow of time. Time has a direction. We remember the past, but not the future. Eggs break, but don't spontaneously reassemble. The universe becomes more disordered over time. This directionality is called the arrow of time. But here's the weird part. The fundamental laws of physics don't distinguish between past and future. If you filmed particles interacting and played the video backward, you couldn't tell the difference. The laws work the same in both directions. So where does the arrow of time come from? The answer is entropy, the measure of disorder. The second law of thermodynamics says entropy always increases. This gives time its direction. But why was entropy low at the Big Bang? That's one of the deepest mysteries in physics. The early universe was in an incredibly ordered state, all matter and energy concentrated in a tiny region. Since then, entropy has been increasing and will continue to increase until the universe reaches maximum entropy in the far future. The arrow of time points from the ordered past to the disordered future, and we're riding that arrow, unable to turn back. Time dilation in your daily life. You might think time dilation is only relevant for astronauts and physicists, but it affects you every day in subtle ways. When you drive a car, you experience time dilation. At highway speeds, your clock runs slower than a stationary clock by about 1 part in a trillion. Over a lifetime of driving, you age about 1 microsecond less than if you'd stayed still. When you climb stairs, you experience gravitational time dilation. Your head ages faster than your feet by billionths of a second. When you fly in an airplane, both effects combine. You're moving fast, time slows, and you're at high altitude, time speeds up. For typical commercial flights, the altitude effect wins, so you age slightly faster when flying. These effects are tiny, but they're real. Every moment of your life, time is flowing at a slightly different rate, depending on your motion and position in Earth's gravitational field. The relativity of simultaneity. Here's another mind-blowing consequence of relativity. Events that are simultaneous for one observer may not be simultaneous for another. Imagine 2 lightning bolts strike the front and back of a moving train at the same time, as measured by someone standing on the platform. For that person, the strikes are simultaneous. But for someone on the train, moving toward one strike and away from the other, the strikes are not simultaneous. They see the front strike first, then the back strike. Both observers are correct. There is no absolute simultaneity. Whether 2 events happen at the same time depends on your frame of reference. This means the concept of now is relative. Events happening right now on a distant planet depend on your motion. Change your velocity, and you change which distant events are happening now. The universe doesn't have a universal present moment. Now is local, personal, and relative. Time crystals, breaking time. Symmetry. In 2012, Nobel laureate Frank Wilczek proposed a bizarre new state of matter: time crystals. These are structures that repeat in time the way ordinary crystals repeat in space. A normal crystal, like diamond, has atoms arranged in a repeating pattern in space. A time crystal has a pattern that repeats in time, oscillating between states without expending energy. This seemed impossible. It would violate the laws of thermodynamics. But in 2017, 2 teams of physicists created time crystals in the lab. They used chains of ions or atoms, hitting them with laser pulses. The system settled into states that oscillated with a period twice as long as the driving pulses. Time crystals break time translation symmetry, the idea that the laws of physics are the same at all times. They represent a new phase of matter that exists in a perpetual state of change. What are time crystals good for? Potentially quantum computing, ultra-precise sensors, and new ways to store information. But mostly, they're just mind-blowingly weird. The block universe. Some interpretations of relativity suggest that past, present, and future all exist simultaneously in a block universe. Time is just another dimension, like space. The universe is a 4-dimensional block, and our experience of time passing is an illusion created by our consciousness moving through the block. In this view, your birth, your current moment, and your death all exist right now in different parts of the block. The future is already there, waiting for you to experience it. The past still exists, just in a different part of space-time. This is called eternalism, and it's a philosophically challenging idea. It suggests free will might be an illusion. If the future already exists, how can we change it? It also suggests that time passing is subjective, a feature of consciousness rather than reality. Not all physicists accept the block universe interpretation, but it's consistent with relativity, and it forces us to reconsider our most basic assumptions about time and reality. Conclusion: time is stranger than fiction. Time doesn't work the way you think. It's not universal, constant, or absolute. It flows at different rates depending on motion and gravity. It had a beginning. It has a direction. It might be an illusion. Every fact in this chapter is real, tested, and verified. GPS satellites prove relativity daily. Atomic clocks measure time dilation. Astronauts travel to the future. Black holes stop time. The universe is stranger than we imagined, and time is at the heart of that strangeness. As we continue our journey through mind-blowing space facts, remember this: the most fundamental thing you thought you understood, time itself, is far weirder than you ever dreamed. The cosmic emptiness. Here's a fact that will change how you see reality. You're mostly empty space, so is everything around you. In fact, the entire universe is mostly nothing. If an atom were the size of a football stadium, the nucleus would be a marble at the center, and the electrons would be tiny specks orbiting at the outer walls. Everything in between? Empty space. The solid matter you're made of is 99.9% empty space, but it gets weirder. Even that tiny amount of stuff, the protons, neutrons, and electrons, isn't really solid. Quantum mechanics tells us particles are more like probability clouds than little balls, and most of the universe isn't even made of this kind of matter at all. Welcome to the cosmic void, where nothing is something, and everything is mostly nothing. Dark matter, the invisible universe. Here's a mind-blowing fact. Everything you can see, stars, galaxies, planets, gas clouds, even light itself, makes up only 5% of the universe. The other 95%? We can't see it, touch it, or directly detect it. About 27% of the universe is dark matter, mysterious stuff that doesn't emit, absorb, or reflect light. We know it exists only because of its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than we can see. The universe's large-scale structure requires more gravity than visible matter provides. Dark matter is everywhere. Right now, dark matter particles are passing through your body, billions of them every second. They pass through Earth, through the sun, through everything, barely interacting with normal matter at all. We don't know what dark matter is. Leading candidates include WIMPs, weakly interacting massive particles, axions, and primordial black holes. Despite decades of searching, we haven't directly detected dark matter particles. It's the universe's greatest hide-and-seek champion. Dark energy, the cosmic accelerator. If dark matter is weird, dark energy is weirder. It makes up 68% of the universe, more than twice as much as dark matter, and we have even less idea what it is. Dark energy is the name we give to whatever is causing the universe's expansion to accelerate. In the 1990s, astronomers discovered that distant supernovae were dimmer than expected, indicating the universe's expansion is speeding up, not slowing down. This was shocking. Gravity should slow expansion, not speed it up. Something must be pushing space apart, working against gravity. We call it dark energy, but that's just a placeholder name for our ignorance. Dark energy might be the cosmological constant, a property of space itself, where empty space has energy. Or it might be a dynamic field called quintessence. Or it might be a sign that our understanding of gravity is wrong. Whatever it is, dark energy dominates the universe's energy budget and determines its ultimate fate. And we have no idea what it is. The void. Between galaxies. Space between stars is mostly empty, about 1 atom per cubic centimeter, but space between galaxies is even emptier, about 1 atom per cubic meter. That's 1,000,000 times less dense. These cosmic voids are the largest structures in the universe, spanning hundreds of millions of light years. They contain very few galaxies, very little gas, and almost no stars. They're the emptiest places in existence, but even voids aren't completely empty. They contain dark matter, dark energy, and a thin web of gas, and they're expanding, pushed apart by dark energy, becoming even emptier over time. In the far future, as the universe continues to expand and accelerate, these voids will grow. Eventually, galaxies will be so far apart that beings in one galaxy won't be able to see any others. The universe will appear to be just one galaxy surrounded by infinite emptiness. Quantum vacuum, not really empty. Here's where things get really weird. Even empty space isn't truly empty. Quantum mechanics tells us that vacuum is seething with activity. According to the Heisenberg uncertainty principle, energy can fluctuate for brief moments. This creates virtual particle pairs. A particle and its antiparticle that pop into existence exist for a tiny fraction of a second and then annihilate each other. This isn't speculation. The Casimir effect proves it. Place 2 metal plates very close together in a vacuum, and they'll be pushed together by a measurable force. Why? Virtual particles with wavelengths larger than the gap can't exist between the plates, but they can exist outside. This creates a pressure difference that pushes the plates together. The quantum vacuum has energy, lots of it. When physicists calculate how much energy the quantum vacuum should have, they get an absurdly large number, 10 or 120 times larger than the dark energy we observe. This is called the cosmological constant problem, and it's one of the biggest unsolved problems in physics. Your mostly empty space. Let's return to atoms. An atom is about 10 meters across. The nucleus is about 15 meters across, 100,000 times smaller. If the nucleus were a marble, the atom would be a kilometer wide. The electrons orbiting the nucleus don't fill this space. They're point particles, as far as we know, with no size at all. They exist as probability clouds, more likely to be found in certain regions, but they don't occupy space the way a solid object does. So what makes matter feel solid? The answer is electromagnetic force. When you touch a table, you're not really touching it. The electrons in your hand's atoms repel the electrons in the table's atoms. You feel this repulsion as solidity. You've never actually touched anything. You've only felt electromagnetic repulsion. You're floating through life, separated from everything by tiny gaps of empty space, held up by invisible forces. The observable universe is tiny. The observable universe, the part we can see, is about 93 billion light-years across. That sounds huge, but it might be infinitesimally small compared to the whole universe. If the universe is infinite, which it might be, then the observable universe is literally 0% of the total. An infinite universe contains infinite galaxies, infinite stars, infinite planets, and infinite copies of you. Even if the universe is finite, it's probably much larger than the observable part. Inflation theory suggests the universe expanded exponentially in its first fraction of a second, growing from subatomic size to potentially many times larger than the observable universe. We can only see the part of the universe where light has had time to reach us since the Big Bang. Beyond that is more universe, potentially infinite, that we can never observe. Most stars have never been seen. There are about 200 billion trillion stars in the observable universe, 2 × 10⁻23. That's more stars than grains of sand on all Earth's beaches. But most of these stars are so far away that their light hasn't reached us yet, or is too dim to see. Of the stars we can see with the naked eye, about 5,000 on a dark night, all are in our galaxy, and most are within a few hundred light years. The Milky Way contains 200 to 400 billion stars. We've directly observed only a tiny fraction. Most stars in our galaxy have never been seen by human eyes and never will be. They're too dim, too distant, or hidden behind dust clouds. And that's just our galaxy. There are about 2 trillion galaxies in the observable universe. Most contain billions to trillions of stars. The vast majority of stars in the universe will never be observed by anyone. The Great Attractor. Something massive is pulling our galaxy, and millions of others, toward it at 600 kilometers per second. We call it the Great Attractor, and we can't see it directly because it's hidden behind the Milky Way's disk. The Great Attractor is a gravitational anomaly in intergalactic space, about 250 million light-years away. It's pulling the Milky Way, Andromeda, and thousands of other galaxies toward it. But the Great Attractor itself is being pulled by something even larger, the Shapley supercluster, a massive concentration of galaxies 650 million light-years away containing about 8,000 galaxies. We're falling through space, pulled by invisible mass concentrations on a journey that will take hundreds of millions of years. And we only discovered this in the 1970s. The Reiki, cosmic voids and walls. The universe's large-scale structure looks like a cosmic web, filaments of galaxies separated by enormous voids. This structure formed from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. The largest known structure is the Hercules Corona Borealis Great Wall, a galactic filament about 10 billion light-years long. It's so large, it challenges our understanding of cosmology. Structures this big shouldn't exist according to some models. Between these walls and filaments are voids, vast empty regions with very few galaxies. The largest known void, the Bootes void, is about 330 million light-years across and contains only about 60 galaxies compared to the 2s expected for that volume. These structures are so large that light takes hundreds of millions of years to cross them. They're the universe's architecture, shaped by dark matter and dark energy over cosmic time. Dumbreuer's conclusion: embracing the void. The universe is mostly nothing. Dark matter and dark energy make up 95% of everything, and we don't know what they are. The space between galaxies is nearly empty. Even atoms are mostly empty space. But this emptiness isn't passive. It's dynamic, expanding, filled with dark energy and quantum fluctuations. It's pulling galaxies together and pushing the universe apart. It's the stage on which cosmic drama unfolds. Understanding that we're mostly nothing doesn't diminish us. It reveals the incredible forces and fields that hold us together, the quantum mechanics that makes matter possible, and the cosmic web that connects everything. We're islands of complexity in an ocean of emptiness, and that makes us all the more remarkable. The illusion of standing still. Right now, as you read this, you feel stationary. You're sitting or standing, perhaps in a chair or on a couch, feeling perfectly still. But here's the mind-blowing truth. You're moving through space at millions of kilometers per hour. You're spinning with Earth's rotation. You're orbiting the sun. You're circling the galaxy. You're being pulled toward the Great Attractor. You're moving with the local group of galaxies. And all of this is happening simultaneously, right now, as you sit still. By the time you finish reading this chapter, you'll have traveled hundreds of thousands of kilometers through space. You've never been still for a single moment of your life. None of us have. Welcome to the cosmic motion that never stops. Dumbreuer, Earth's rotation, the first layer of motion. Let's start with the most obvious motion, Earth's rotation. Our planet spins on its axis once every 24 hours, creating day and night. But how fast is this spin? At the equator, Earth's surface moves at about 1,670 kilometers per hour. 137 miles per hour. That's faster than the speed of sound. If you're standing at the equator, you're moving at supersonic speeds right now, just from Earth's rotation. But here's the catch. The speed decreases as you move toward the poles. At 45 degrees latitude, roughly the latitude of Minneapolis, Milan, or Montreal, you're moving at about 180 kilometers h. At the poles, you're barely moving at all, just spinning in place once per day. This rotation creates the Coriolis effect, which makes hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It affects ocean currents, wind patterns, and even the trajectory of long-range artillery shells. The rotation also makes Earth bulge at the equator. Our planet isn't a perfect sphere, it's an oblate spheroid, about 43 kilometers wider at the equator than from pole to pole. This bulge is caused by a centrifugal force from the rotation. And here's something wild. Earth's rotation is slowing down. Tidal forces from the moon are gradually breaking Earth's spin. About 620 million years ago, a day was only 21.9 hours long. In the far future, Earth's rotation will slow until one side permanently faces the moon, just as the moon already shows only one face to Earth. Orbiting the Sun, 107,000 kilometers per hour. Earth's rotation is just the beginning. Our planet is also orbiting the Sun at an average speed of 107,000 kilometers per hour, 6,600 miles per hour. That's about 30 kilometers per second. Think about that. Every second, Earth moves 30 kilometers through space. In the time it takes you to read this sentence, Earth has traveled about 150 kilometers in its orbit around the Sun. Earth's orbit isn't a perfect circle, it's an ellipse. We're closest to the Sun, perihelion, in early January, about 147 million kilometers away. We're farthest, aphelion, in early July, about 152 million kilometers away. This 5 million kilometer difference affects Earth's orbital speed. We move faster when closer to the Sun, about 30.3 km/s, and slower when farther away, about 29.3 km/s. Interestingly, Earth is closest to the Sun during Northern Hemisphere winter. This proves that seasons aren't caused by distance from the Sun, but by the tilt of Earth's axis. When the Northern Hemisphere is tilted toward the Sun, it's summer there, even though Earth is farther from the Sun. The orbital motion also creates stellar parallax, the apparent shift in star positions as Earth moves around the Sun. Ancient astronomers couldn't detect this parallax, which led some to believe Earth was stationary. We didn't measure stellar parallax until 1838, finally proving Earth orbits the Sun. The Solar System's galactic orbit, 828,000 kilometers per hour. But Earth's motion around the Sun is just one part of a much larger motion. Our entire solar system is orbiting the center of the Milky Way galaxy at about 828,000 kilometers per hour, 514,000 miles per hour. That's about 230 kilometers per second. At this speed, the solar system takes about 250 million years to complete one orbit around the galactic center. This period is called a galactic year or cosmic year. Since Earth formed 4.6 billion years ago, our planet has completed only about 20 orbits around the galaxy. The last time we were at this position in our galactic orbit, dinosaurs were just beginning to dominate Earth. The time before that, the supercontinent Pangaea was forming. Each galactic year brings dramatic changes to Earth. The solar system doesn't orbit in a flat plane. We bob up and down relative to the galactic disk, crossing through the disk plane every 30-35 million years. Some scientists have proposed that these crossings might correlate with mass extinction events on Earth, possibly due to increased comet impacts or cosmic ray exposure. This hypothesis is controversial and not widely accepted, but it's a fascinating possibility. Our position in the galaxy is also special. We're in the Orion Arm, a minor spiral arm between the larger Sagittarius and Perseus arms. We're about 26,000 light-years from the galactic center, far enough to avoid the intense radiation and gravitational chaos near the center, but not so far that we're in the galactic boonies. The Milky Way's motion, 2.1 million kilometers per hour. The Milky Way itself isn't stationary. Our galaxy is moving through space at about 2.1 million kilometers per hour, 1.3 million miles per hour, relative to the cosmic microwave background radiation, the afterglow of the Big Bang. This motion has several components. First, the Milky Way and Andromeda are falling toward each other at about 110 kilometers per second. They'll collide in about 4-5 billion years, merging to form a giant elliptical galaxy that astronomers have nicknamed Milkomeda. Second, the Milky Way, Andromeda, and about 54 other galaxies form the local group, which is being pulled toward the Virgo cluster, a massive collection of about 1,500 galaxies located about 65 million light-years away. Third, the Virgo cluster itself, along with other nearby galaxy clusters, is being pulled toward an even larger structure called the Great Attractor, a gravitational anomaly about 250 million light-years away in the direction of the constellations Hydra and Centaurus. And fourth, the Great Attractor is being pulled toward the Shapley supercluster, an enormous concentration of galaxies about 650 million light-years away containing about 8,000 galaxies. All of these motions combine to give the Milky Way its total velocity through space. We're falling through the universe in a complex dance of gravitational attraction, pulled by massive structures we can barely see. The Great Attractor falling through space at 600 kilometers per second. Let's focus on the Great Attractor for a moment, because it's one of the strangest discoveries in astronomy. In the 1970s, astronomers noticed something odd. Galaxies in our region of space weren't moving the way they should if the universe's expansion were uniform. Instead, they were all flowing in one direction, as if being pulled by something massive. This something is the Great Attractor. It's pulling our galaxy, along with thousands of others, toward it at about 600 kilometers per second. That's 2.16 million kilometers per hour. The problem is, we can't see the Great Attractor directly. It's located behind the zone of avoidance, the region of sky blocked by the Milky Way's disk. Dust and stars in our galaxy's disk block our view of whatever is pulling us. Using radio and infrared observations that can penetrate the dust, astronomers have mapped the region. They found the Norma cluster, a massive galaxy cluster that might be part of the Great Attractor. But the full structure remains mysterious. What we do know is that we're falling toward it. And we have been for billions of years. This motion is in addition to the universe's expansion. We're being pulled toward the Great Attractor even as space itself expands. Adding it all up, your total velocity. Let's add up all these motions to find your total velocity through space. 1. Earth's rotation. 1,670 km at equator. 2. Earth's orbit around Sun. 17,000 km. 3. Solar System's orbit around galaxy. 828,000 km. 4. Milky Way's motion through space. 100,000 km. But you can't simply add these numbers because they are in different directions. Velocity is a vector. It has both magnitude and direction. To find your total velocity, you need to add these vectors. When astronomers do this calculation relative to the cosmic microwave background, the closest thing we have to an absolute reference frame, they find that our solar system is moving at about 370 kilometers per second, or 1.3 million kilometers per hour. That means in the time it took you to read this section, about 2 minutes, you've traveled about 44,000 kilometers through space. That's more than Earth's circumference. There's no such thing as standing still. Here's a profound realization. There's no such thing as absolute rest in the universe. You can't stand still because there's no universal reference frame to be still relative to. Einstein's theory of relativity tells us that all motion is relative. You can only measure your velocity relative to something else. Relative to Earth, you might be stationary. Relative to the Sun, you're moving at 107,000 km/h. Relative to the galactic center, you're moving at 828,000 km/h. Relative to the cosmic microwave background, you're moving at 1.3 million km/h. None of these reference frames is more correct than the others. Motion is always relative. The universe has no preferred reference frame, no cosmic at-rest position. This has philosophical implications. The ancient Greek idea of the unmoved mover, something that causes motion without itself moving, doesn't make sense in our universe. Everything moves. Motion is fundamental to existence. The cosmic reference frame. While there's no absolute rest, there's something close, the cosmic microwave background, CMB rest frame. The CMB is the afterglow of the Big Bang, Radiation that has been traveling through space for 13.8 billion years. It's remarkably uniform in all directions, the same temperature, 2.725 Kelvin, everywhere in the sky. But it's not perfectly uniform. When we measure it precisely, we see a dipole pattern. It's slightly hotter in one direction and slightly cooler in the opposite direction. This is due to our motion relative to the CMB. We're moving toward the hotter region and away from the cooler region, creating a Doppler shift. By measuring this dipole, astronomers determined that our solar system is moving at 370 km/s relative to the CMB rest frame. This is as close as we can get to measuring our absolute velocity through space. The CMB rest frame is special because it's the same everywhere in the universe. Any observer, anywhere, can measure their velocity relative to the CMB. It's the closest thing we have to a universal reference frame. You've traveled farther than you think. Let's put this in perspective. You're probably sitting down reading this. You feel stationary. But in the time it takes to read this chapter, about 15 minutes, you've traveled. Earth's rotation. 25,000 kilometers at equator. Earth's orbit. 600,000 kilometers. Galactic orbit. 12,400,000 kilometers. Total through space. 33,000 kilometers. That's 33 million kilometers in 15 minutes. You've traveled farther than the distance from Earth to Venus, all while sitting still. In your lifetime, you'll travel trillions of kilometers through space. If you live 80 years, you'll travel about 58 trillion kilometers just from Earth's orbit around the Sun. Add in galactic motion, and you'll travel hundreds of trillions of kilometers. You're not just a passenger on spaceship Earth. You're a cosmic voyager, traveling through the universe at incredible speeds on a journey that began at your birth and will continue until your death. The cosmic speed limit. All this motion raises a question. Is there a limit to how fast we can move? Yes. Einstein's special relativity tells us that nothing can move faster than light in a vacuum. 299,192 kilometers per second, about 1.8 billion km/h. This isn't just a speed limit for matter. It's a fundamental property of space-time itself. As you approach light speed, strange things happen. Time slows down for you relative to stationary observers. Your mass increases. Distances contract in your direction of motion. At exactly light speed, time would stop. Your mass would become infinite, and distances would shrink to zero. This is impossible for anything with mass. Only massless particles, like photons, can travel at light speed. Everything else must travel slower. Our motion through space, even at 2.1 million km/h, is only about 0.2% of light speed. We're moving fast by human standards, but we're crawling by cosmic standards. The universe's expansion, the ultimate motion. There's one more motion we haven't discussed, the expansion of space itself. The universe is expanding. Galaxies are moving apart from each other, not because they're moving through space, but because space itself is expanding, carrying galaxies with it. This expansion means that distant galaxies are moving away from us at speeds that increase with distance. Galaxies a billion light-years away are receding at about 22,000 km/s. Galaxies 10 billion light-years away are receding at about 220,000 km/s, faster than light. Wait, didn't we just say nothing can move faster than light? That's true for motion through space, but space itself can expand faster than light. There's no speed limit on the expansion of space. This means there are galaxies we can never reach. Even if we could travel at light speed, they're receding faster than light due to cosmic expansion. We can see them now because their light was emitted when they were closer, but we can never visit them. The expansion is also accelerating, driven by dark energy. Distant galaxies are receding faster and faster. In the far future, galaxies will be so far apart that beings in one galaxy won't be able to see any others. The universe will appear to be just one galaxy surrounded by darkness. Conclusion. Embrace your cosmic journey. You're moving through space at millions of kilometers per hour. You're spinning with Earth, orbiting the Sun, circling the galaxy, falling toward the Great Attractor, and riding the expansion of the universe. You've never been still. You never will be. Motion is your natural state, your cosmic birthright. This motion connects you to the universe. The same forces that move galaxies move you. The same expansion that stretches space carries you along. You're not separate from the cosmos. You're part of its grand motion, its eternal dance. So the next time you sit down to rest, remember, you're not resting. You're traveling through space at incredible speeds on a journey that encompasses the entire universe. You're a cosmic voyager, and your journey is far from over. The hostile void space is beautiful. It's awe-inspiring. It's the final frontier. It's also trying to kill you in more ways than you can imagine. The vacuum of space, the radiation, the temperature extremes, the micrometeorites, the gamma-ray bursts, the rogue black holes. The universe is filled with deadly hazards that would end your life in seconds if you weren't protected by Earth's atmosphere and magnetic field. We live on a fragile oasis in a cosmic shooting gallery. Every moment of your life, Earth is shielding you from a universe that is fundamentally hostile to human life. Let's explore all the ways space wants you dead. The vacuum. Death in 15 seconds. Let's start with the most obvious danger, the vacuum of space. Space isn't completely empty, as we learned in Chapter 2, but it's close enough. The pressure in space is essentially zero, about 10 over 17 atmospheres. What happens if you're exposed to this vacuum without a spacesuit? Hollywood gets this wrong. You don't explode. You don't instantly freeze. You don't die immediately. Here's what actually happens. Jaw 15 seconds. You remain conscious. The air in your lungs expands rapidly. If you hold your breath, your lungs will rupture, potentially fatal. If you exhale and don't try to hold your breath, you might survive this phase. The water on your tongue and in your eyes begins to boil, not from heat, but from low pressure. You'll feel your skin swelling as water vapor forms in your tissues. 15, 30 seconds. You lose consciousness due to lack of oxygen. Your blood doesn't boil, it's protected by your circulatory system's pressure, but oxygen stops reaching your brain. 1 to 8 or 2 minutes. Without oxygen, brain damage begins. This is the point of no return for most people. After 2 minutes, even if you're rescued and repressurized, you'll likely have permanent brain damage or die. The good news? If you're rescued within 15-30 seconds and immediately repressurized, you'll probably survive with no permanent damage. This actually happened in 1965 when a NASA technician's spacesuit accidentally depressurized in a vacuum chamber. He remained conscious for about 14 seconds and fully recovered. The bad news? In actual space, there's no one to rescue you in 15 seconds. It's radiation, the silent killer. If the vacuum doesn't kill you, the radiation will. Space is flooded with radiation from multiple sources, and none of it is good for you. Cosmic rays. These are high-energy particles, mostly protons, traveling at near light speed. They come from supernovae, active galactic nuclei, and other violent cosmic events. When they hit your body, they tear through cells, damaging DNA and increasing cancer risk. On Earth, we're protected by our atmosphere and magnetic field. In space, you're exposed. Astronauts on the International Space Station receive about 150-200 millisieverts of radiation per year, equivalent to about 150-200 chest X-rays. That's 10-20 times more radiation than people on Earth receive. On a mission to Mars, astronauts would receive about 300 millisieverts during the 6-month journey each way, plus whatever they receive on Mars's surface. Mars has no magnetic field and a thin atmosphere. This significantly increases their lifetime cancer risk. Solar radiation. The sun constantly emits a stream of charged particles called the solar wind. During solar flares and coronal mass ejections, this radiation intensifies dramatically. A major solar event could deliver a lethal dose of radiation to unprotected astronauts. In August 1972, between the Apollo 16 and Apollo 17 missions, a massive solar flare erupted. If astronauts had been on the moon during this event, they would have received a potentially lethal radiation dose. Van Allen radiation belts. Earth is surrounded by 2 donut-shaped regions of intense radiation trapped by our magnetic field. These belts contain high-energy protons and electrons. Spacecraft must either pass through them quickly or avoid them entirely. Prolonged exposure would be fatal. The radiation in space doesn't just increase cancer risk. It can cause acute radiation sickness, damage the central nervous system, increase cardiovascular disease risk, and accelerate aging. It's one of the biggest challenges for long-duration space missions. Temperature from absolute zero to millions of degrees. Space has no temperature in the traditional sense. Temperature is a measure of molecular motion, and space has very few molecules, but objects in space can experience extreme temperatures. In shadow. Without sunlight, objects in space can cool to near absolute zero, 204 degrees or 459 degrees F. The cosmic microwave background radiation provides a baseline temperature of 2.7 Kelvin, 270 G, but objects can radiate heat and become even colder. In sunlight, direct sunlight in space is intense. Without an atmosphere to filter it, the sun's radiation can heat objects to over 120 degrees, 250 degrees, on the side facing the sun. The moon's surface reaches 127 degrees Celsius in direct sunlight. The challenge. The problem isn't just the extremes, it's the rapid transitions. On the ISS, which orbits Earth every 90 minutes, spacecraft experience 45 minutes of sunlight, followed by 45 minutes of darkness. Temperatures swing from about 120 degrees to 150 degrees every orbit. This thermal cycling stresses materials and requires sophisticated thermal management systems. For humans, maintaining body temperature in space is challenging. You can't rely on convection, no air, or conduction, nothing to touch. You can only radiate heat. Spacesuits must carefully balance heat retention and heat dissipation to keep astronauts comfortable. Micrometeorites, cosmic bullets. Space is filled with debris, rocks, dust, and ice traveling at incredible speeds. These micrometeorites pose a serious threat to spacecraft and astronauts. The average impact velocity in Earth orbit is about 10 kilometers per second, 36,000 kilometers per h or 22,000 mph. Some impacts occur at up to 20 kilometers per h. At these speeds, even tiny particles carry enormous energy. A 1-gram particle, about the mass of a paperclip, traveling at 10 kilometers per h, has the kinetic energy of a bowling ball dropped from a 5-story building. A 10-gram particle has the energy of a car traveling at highway speed. The ISS is hit by small particles constantly. Its windows must be replaced regularly due to micrometeorite damage. The station has shields designed to protect against particles up to 1 centimeter in diameter. Larger objects are tracked, and the ISS performs collision avoidance maneuvers when necessary. In 2016, a tiny paint fleck hit an ISS window, creating a 7-millimeter chip. Paint flecks are common in orbit. They're debris from spacecraft that have flaked off over time. Even something as small as a paint fleck becomes a dangerous projectile at orbital velocities. For astronauts on spacewalks, micrometeorites are a constant risk. Spacesuits have multiple layers to protect against small impacts, but a large enough particle could puncture the suit, causing rapid depressurization. Gamma-ray bursts, cosmic extinction events. Gamma-ray bursts, GRBs, are the most energetic events in the universe since the Big Bang. They occur when massive stars collapse into black holes or when neutron stars merge. For a few seconds, a GRB can outshine the entire rest of the universe in gamma rays. If a GRB occurred within a few thousand light-years of Earth and was pointed at us, it could cause a mass extinction. The gamma rays would strip away Earth's ozone layer, exposing the surface to lethal solar ultraviolet radiation. This could trigger a global ecological collapse. The good news? GRBs are rare and directional. They only affect a narrow cone of space. The odds of one hitting Earth are very low, perhaps once every few 100 million years. The bad news? We'd have no warning. GRBs travel at the speed of light. The first sign of a GRB would be its arrival. By the time we detected it, it would already be affecting us. Some scientists have proposed that a GRB might have caused the Ordovician extinction event 450 million years ago, which killed about 85% of marine species. This is speculative, but it's a reminder that space can reach out and touch us in devastating ways. Solar flares and coronal mass ejections. The sun is generally friendly to life on Earth, but it has a violent side. Solar flares and coronal mass ejections, CMEs, can release enormous amounts of energy and particles into space. A solar flare is a sudden flash of increased brightness on the sun, releasing energy equivalent to millions of nuclear bombs. A CME is an eruption of plasma and magnetic field from the sun's corona, hurling billions of tons of material into space at millions of kilometers per hour. When a CME hits Earth, it compresses our magnetic field, inducing electric currents in power grids, pipelines, and communication systems. A large enough CME can cause widespread blackouts and damage transformers. The Carrington event of 1859 was the largest recorded geomagnetic storm. Telegraph systems worldwide failed, some operators received electric shocks, and auroras were visible as far south as the Caribbean. If a similar event occurred today, it could cause trillions of dollars in damage and knock out power grids for months. In space, astronauts are more vulnerable. A major solar event could deliver a lethal radiation dose. The ISS has a shielded area where astronauts can shelter during solar storms, but astronauts on the Moon or Mars would have limited protection. Rogue black holes. Black holes are dangerous enough when they're stationary, but some black holes are rogue, ejected from their home galaxies and wandering through space. When two galaxies merge, their central supermassive black holes eventually merge too. This merger releases enormous energy in gravitational waves, which can give the resulting black hole a kick, ejecting it from the galaxy at speeds up to 5,000 kilometers. There could be millions of rogue supermassive black holes wandering through intergalactic space. If one passed through our galaxy, it could gravitationally disrupt star systems, potentially ejecting planets from their orbits. The odds of a rogue black hole passing near our solar system are incredibly low. But it's not zero, and we'd have limited warning. Black holes are invisible unless they're actively accreting matter. Hypervelocity, stars. Some stars are moving so fast they're escaping the Milky Way. These hypervelocity stars traveling at 1,000 km/s were likely ejected by interactions with the supermassive black hole at our galaxy's center. If a hypervelocity star passed through our solar system, its gravitational influence could perturb planetary orbits, potentially sending comets from the Oort cloud into the inner solar system. This could trigger a bombardment of Earth. Again, the odds are very low, but space is full of these low-probability, high-consequence threats. The Kessler Syndrome. This one is our fault. The Kessler Syndrome is a cascade of collisions in Earth orbit. As more satellites are launched, the risk of collisions increases. When satellites collide, they create debris. This debris can hit other satellites, creating more debris in a runaway chain reaction. If the Kessler Syndrome occurs, Earth orbit could become unusable for decades or centuries. We'd be trapped on our planet, unable to launch satellites or spacecraft through the debris field. We're already seeing the early stages. There are over 34,000 pieces of tracked debris, larger than 10 centimeters in orbit, and millions of smaller pieces. Several major collisions have already occurred, including the 2009 collision between an active Iridium satellite and a defunct Russian satellite. Space agencies are developing debris removal technologies, but it's a race against time. The more debris we create, the harder it becomes to clean up. Earth's protective shield. Despite all these dangers, life on Earth thrives. Why? Because Earth has multiple layers of protection. The atmosphere blocks most radiation, burns up most meteorites, maintains pressure, and regulates temperature. The magnetic field deflects the solar wind and cosmic rays, preventing them from stripping away our atmosphere. The ozone layer blocks harmful ultraviolet radiation from the sun. The moon stabilizes Earth's axial tilt, preventing extreme climate swings. Jupiter acts as a cosmic vacuum cleaner, deflecting or capturing many comets and asteroids that might otherwise hit Earth. Remove any of these protections, and Earth becomes much more hostile to life. Mars lost its magnetic field billions of years ago, and its atmosphere was stripped away by the solar wind. Venus has a thick atmosphere, but no magnetic field, and its surface is a hellish 460 degrees Celsius. Earth is a Goldilocks planet, just right for life, and a big part of that is its protection from the hostile universe beyond. Conclusion: appreciate your atmosphere. Space is trying to kill you. The vacuum, the radiation, the temperature extremes, the micrometeorites, the gamma-ray bursts. The universe is fundamentally hostile to human life. But you're safe. Right now, as you read this, Earth's atmosphere and magnetic field are protecting you from all these threats. You're breathing air at comfortable pressure. You're shielded from lethal radiation. You're at a comfortable temperature. You're protected from cosmic bullets. Don't take it for granted. Earth is a rare sanctuary in a dangerous universe. Every breath you take is a gift from the thin layer of air that separates you from the void. And when you look up at the stars, remember, they're beautiful, but they're also deadly. Space is not our natural environment. We're creatures of Earth, adapted to its protection. Venturing into space requires technology, planning, and respect for the dangers that await. Space is trying to kill you, but Earth is keeping you alive. Beyond imagination, the universe contains objects so strange, so extreme, that they challenge our understanding of physics and reality itself. Objects where a teaspoon of matter weighs as much as a mountain. Objects with magnetic fields trillions of times stronger than Earth's. Objects that outshine entire galaxies. Objects that shouldn't exist according to our theories, yet do. These aren't science fiction. They're real, observed, and studied by astronomers. They push the boundaries of what's possible, revealing a universe far stranger than we ever imagined. Welcome to the cosmic zoo of the bizarre. Neutron stars, cities made of nuclei. Imagine compressing the entire mass of the Sun into a sphere the size of a city, about 20 kilometers across. That's a neutron star. Neutron stars are the collapsed cores of massive stars that exploded as supernovae. When a star's core collapses, protons and electrons are squeezed together so tightly they merge into neutrons. The result is the densest stable matter in the universe. The numbers are insane. Density, about 4 ekenot 1017 km3, 400 trillion times denser than water. A teaspoon of neutron star material weighs about 4 billion tons. Surface gravity, 200 billion times stronger than Earth's. If you dropped an object from 1 meter above the surface, it would hit at 7 million km/h. The surface of a neutron star is incredibly smooth. Any mountain would be at most a few millimeters tall, crushed flat by the intense gravity. The surface is probably a crystalline lattice of iron nuclei, the strongest material in the universe. Below the surface, things get weirder. The outer crust is made of nuclei and electrons. Deeper, nuclei merge into exotic shapes, rods, sheets, and tubes called nuclear pasta. Yes, really, astronomers have a sense of humor. At the core, neutrons might break down into quarks, creating quark matter. Neutron stars rotate incredibly fast, up to 700 times per second. This is because of conservation of angular momentum. As the star's core collapsed, it spun faster, like a figure skater pulling in their arms. The fastest known pulsar, PSR J148 2446 AD, rotates 716 times per second. Its equator is moving at about 24% the speed of light. Magnetars, the universe's strongest magnets. Take a neutron star and give it a magnetic field 1,000 times stronger. Now you have a magnetar. Magnetars have magnetic fields of 1014 to 1015 Gauss, about a quadrillion times stronger than Earth's magnetic field. These are the strongest magnetic fields in the universe. How strong is that? If you were within 1,000 kilometers of a magnetar, its magnetic field would be lethal. It would disrupt the electromagnetic forces holding your atoms together. You would literally be torn apart at the molecular level. The magnetic field is so strong it warps the shape of atoms, making them elongated like cigars. It affects the vacuum of space itself, creating bizarre quantum effects. Magnetars occasionally have starquakes, the solid crust cracks and shifts, releasing enormous bursts of energy. In December 2004, a magnetar 50,000 light-years away had a starquake that briefly affected Earth's ionosphere. For a tenth of a second, this object 50,000 light-years away was brighter in gamma rays than the full moon. If that magnetar had been 10 light-years away instead of 50,000, it would have caused a mass extinction on Earth. Pulsars, cosmic lighthouses. Pulsars are rotating neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse. If Earth is in the path of the beam, we see regular pulses of radiation. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. The pulses were so regular, arriving every 1/337 seconds, that astronomers briefly wondered if they were signals from an alien civilization. They jokingly called the source LGM-1, Little Green Men 1. We now know of over 3,000 pulsars. They're incredibly precise clocks. Some are more accurate than atomic clocks. The millisecond pulsar PSR J04374715 has a period of 5.757 milliseconds, and it's so stable that astronomers use it to test Einstein's general relativity. Pulsars can be used for navigation. NASA is developing a pulsar GPS system for spacecraft, using pulsar timing to determine position anywhere in the solar system with precision of a few kilometers. Some pulsars are in binary systems, orbiting other stars or even other pulsars. The Hulse-Taylor binary pulsar, discovered in 1974, consists of two neutron stars orbiting each other. Their orbit is decaying due to gravitational wave emission, exactly as predicted by general relativity. This discovery won the Nobel Prize and provided the first indirect evidence for gravitational waves. Quasars, galactic beacons. Quasars are the brightest persistent objects in the universe. A typical quasar outshines an entire galaxy of 200 billion stars, despite being smaller than our solar system. Quasars are powered by supermassive black holes with masses of millions to billions of suns, actively feeding on matter. As matter spirals into the black hole, it forms an accretion disk that heats to millions of degrees, emitting enormous amounts of radiation. The brightest known quasar, TON 618, has a black hole with a mass of 66 billion solar masses. It's 140 trillion times more luminous than the Sun. If it were 30 light-years from Earth, the distance to some nearby stars, it would appear as bright as the Sun in our sky. Quasars are mostly found in the distant universe, meaning they existed billions of years ago. They were common when the universe was young, but rare today. This tells us that supermassive black holes were actively feeding in the early universe, but most have since run out of nearby matter to consume. Some quasars emit jets of matter at nearly the speed of light, extending for millions of light-years. These jets are powered by the black hole's rotation and magnetic field, channeling matter and energy into narrow beams. When a jet points toward Earth, we see a blazar, an extremely bright and variable source. Black holes, holes in reality. Black holes are regions where gravity is so strong that nothing, not even light, can escape. They're not objects in the traditional sense, they're holes in space-time itself. Stellar mass, black holes. Formed when massive stars collapse, masses range from about 3 to 100 solar masses. There are probably 100 million stellar mass black holes in the Milky Way, but we've only detected a few dozen. They're invisible unless they're feeding. Supermassive black holes. Found at the centers of most galaxies, masses range from millions to billions of solar masses. The Milky Way's central black hole, Sagittarius AI, has a mass of 4 million suns. The largest known black hole, TON 618, has a mass of 66 billion suns. Intermediate mass black holes. Hypothetical black holes with masses between stellar and supermassive. We've found a few candidates, but their existence and formation mechanism are still debated. Primordial black holes. Hypothetical black holes that formed in the early universe from density fluctuations. They could have any mass from microscopic to supermassive. Some scientists think primordial black holes might be dark matter. The event horizon of a black hole is the point of no return. Cross it, and you can never escape. For a stellar mass black hole, crossing the event horizon would be violent. Tidal forces would stretch you into a long, thin shape, a process called spaghettification. For a supermassive black hole, you might not even notice crossing the horizon. The tidal forces are weaker for larger black holes. At the center of a black hole is the singularity, a point of infinite density where the laws of physics break down. We don't know what really happens there. General relativity predicts a singularity, but quantum mechanics suggests something else might occur. We need a theory of quantum gravity to understand black hole interiors. Rogue planets, wanderers in darkness. Not all planets orbit stars. Some drift through interstellar space, ejected from their home systems by gravitational interactions. These rogue planets wander the galaxy in eternal darkness. We've discovered dozens of rogue planets, and there might be billions in the Milky Way, possibly more rogue planets than stars. They're hard to detect because they emit almost no light. We find them through gravitational microlensing, when they pass in front of a background star and briefly magnify its light, or by detecting their faint infrared glow. Some rogue planets might be habitable. If a planet has a thick atmosphere and geothermal heat from radioactive decay, it could maintain liquid water beneath an icy surface even without a star. Life might exist in these dark oceans, never knowing the light of a sun. Imagine a civilization on a rogue planet. Their sky would be filled with stars, but they would have no sun, no day-night cycle, no seasons. Their world would be lit only by artificial light or bioluminescence. They might not even know that most planets orbit stars. The Veers, hypervelocity stars, cosmic speedsters. Most stars in the galaxy orbit at a few hundred kilometers per second. But some stars are moving much faster, over 1,000 km/s, fast enough to escape the galaxy entirely. These hypervelocity stars were likely ejected by the supermassive black hole at the galaxy's center. When a binary star system passes close to the black hole, one star can be captured while the other is flung away at incredible speed. The fastest known star, S5HVS1, is moving at 1/5 over 6 million km/h. It will escape the Milky Way and spend eternity wandering intergalactic space. Imagine being on a planet orbiting a hypervelocity star. You'd watch your galaxy recede behind you, eventually becoming just another fuzzy patch in the sky. You'd be heading into the void between galaxies, a journey lasting billions of years, with no destination. Thorne-Zhitkov objects, stars inside stars. In the 1970s, physicists Kip Thorne and Anna Zhitkov predicted a bizarre type of star, a neutron star inside a giant star. This could form if a neutron star collides with a giant star and spirals into its core. The result would look like a normal red giant from the outside, but have a neutron star at its center instead of a normal core. The neutron star would heat the surrounding layers, creating unusual chemical signatures. For decades, these objects were purely theoretical. But in 2014, astronomers found a candidate, HV 2112, a star in the Small Magellanic Cloud with chemical abundances matching predictions for a Thorne-Zhitkov object. If confirmed, this would be one of the strangest stellar configurations in the universe, a star within a star defying our usual categories. Quasi-stars, black holes, inside stars. Even stranger than Thorne-Zhitkov objects are quasi-stars, hypothetical stars from the early universe with black holes at their cores. In the early universe, before the first stars enriched space with heavy elements, stars could grow much larger than today, perhaps 1,000 to 10,000 solar masses. These massive stars might have collapsed to form black holes while still surrounded by their stellar envelopes. The black hole would feed on the surrounding star, releasing enormous energy. This energy would prevent the rest of the star from collapsing, creating a stable or semi-stable configuration, a black hole inside a star. Quasi-stars would be incredibly luminous, millions of times brighter than the sun, and could explain how supermassive black holes formed so early in the universe's history. We haven't observed any quasi-stars. They would have existed billions of years ago. but they might have left behind intermediate mass black holes that we could detect today. Conclusion: the universe's imagination. The universe is more creative than we are. It produces objects we never imagined, pushing the boundaries of physics to extremes we can barely comprehend. Neutron stars where matter is compressed to nuclear density, magnetars with magnetic fields that warp reality, quasars that outshine galaxies, black holes that tear spacetime, rogue planets wandering in darkness, stars inside stars. These aren't anomalies or errors, they're natural consequences of the laws of physics operating under extreme conditions. They show us what's possible in a universe governed by gravity, quantum mechanics, and relativity. And they remind us that reality is stranger than fiction. The universe doesn't need our imagination. It has its own. The scale problem. Your brain wasn't designed to understand the universe. It evolved to help you navigate a savanna, find food, avoid predators, and interact with other humans. The largest distance your ancestors needed to comprehend was maybe a few days' walk. The largest number they needed to count was maybe a few hundred. The universe doesn't care about your brain's limitations. It's so vast, so incomprehensibly large, that even our best analogies fail. Numbers become meaningless. Comparisons break down. We can write the numbers, we can do the math, but we can't truly grasp the scale. And here's the kicker. The universe might be infinite. The part we can see, the observable universe, might be 0% of the total. An infinite universe contains infinite galaxies, infinite stars, infinite planets, and infinite copies of you. Welcome to the cosmic scale problem, where infinity is just the beginning. The observable universe, 93 billion light years. Let's start with what we can see, the observable universe. This is the region of space from which light has had time to reach us since the Big Bang. The universe is 13.8 billion years old, so you might think the observable universe is 13.8 billion light years in radius. But you'd be wrong. It's actually about 46.5 billion light years in radius, making it 93 billion light years across. How is this possible? Because the universe has been expanding while light traveled toward us. Light from a distant galaxy was emitted when that galaxy was much closer. As the light traveled, space expanded, stretching the distance. By the time the light reaches us, the galaxy is much farther away than it was when the light was emitted. This creates a cosmic horizon, a boundary beyond which we can never see, no matter how long we wait. Light from beyond this horizon hasn't had time to reach us yet, and due to the universe's accelerating expansion, it never will. The observable universe is like a sphere around us, 93 billion light years across. But this isn't the edge of the universe. It's just the edge of what we can see. The actual universe extends far beyond, possibly infinitely. Counting the cosmos, numbers beyond comprehension. How many galaxies are in the observable universe? The latest estimate, based on Hubble Space Telescope deep field observations, is about 2 trillion galaxies. 2 trillion. That's 2,000, 1,000. If you counted one galaxy per second, it would take you 63,000 years to count them all. Each galaxy contains on average about 100 billion stars. Some have fewer. Dwarf galaxies might have only a few million. Some have more. Giant elliptical galaxies might have 100 trillion stars. Multiply it out. 2 trillion galaxies, 100 billion stars per galaxy, Machern 200 billion trillion stars. That's 2x 10 powered 23 stars. Written out, 200,000 stars. This number is larger than all the grains of sand on all the beaches on Earth. It's larger than all the grains of sand in the Sahara Desert. It's probably larger than all the grains of sand on Earth, period. And remember, this is just the observable universe. The actual universe might be infinite, containing infinitely more stars. The cosmic distance ladder. How do we measure these vast distances? Astronomers use a cosmic distance ladder, a series of techniques, each building on the previous one. Step 1. Parallax, up to 10,000 light years. As Earth orbits the Sun, nearby stars appear to shift position relative to distant background stars. This shift, called parallax, can be measured and used to calculate distance. The European Space Agency's Gaia satellite has measured parallax for over 1 billion stars. Step 2. Standard candles, up to 100 million light-years. Some objects have known intrinsic brightness. Cepheid variable stars, for example, pulsate with a period that depends on their luminosity. By measuring the period, we know how bright they should be. By measuring how bright they appear, we can calculate their distance. Step 3. Type Ia supernovae, up to billions of light-years. Type Ia supernovae occur when white dwarfs reach a critical mass and explode. They all have roughly the same intrinsic brightness, making them excellent standard candles for measuring cosmic distances. Step 4. Redshift, to the edge of the observable universe. Due to cosmic expansion, distant galaxies are moving away from us. This stretches their light to longer wavelengths, a redshift. The amount of redshift tells us how much the universe has expanded since the light was emitted, which tells us the distance. Each step of the ladder is calibrated using the previous step. Errors at lower rungs propagate upward, which is why cosmic distance measurements have uncertainties. But the ladder works, giving us a map of the universe. Light years. What they really mean. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers, 588 trillion miles. Let's put this in perspective. Light travels from Earth to Moon in 1.3 seconds. Light travels from Sun to Earth in 8.3 minutes. Light travels from Sun to Pluto in 5.5 hours. Light travels from Sun to nearest star in 4.2 years. The Milky Way is about 100,000 light-years across. Light from one side of our galaxy takes 100,000 years to reach the other side. Andromeda, our nearest large galaxy, is 2.5 million light-years away. The light we see from Andromeda today left when our ancestors were Homo habilis, just learning to use stone tools. The farthest galaxy ever observed, GNZ 11, is 13.4 billion light-years away. We see it as it was just 400 million years after the Big Bang, when the universe was only 3% of its current age. Every time you look at the night sky, you're looking back in time. The stars you see are ghosts, images of how they were years, decades, or centuries ago. Some might already be dead, but we won't know for years or centuries. Beyond the observable, the infinite universe. The observable universe might be just a tiny fraction of the total universe. In fact, if the universe is infinite, which it might be, the observable universe is literally 0% of the total. Why might the universe be infinite? Because it appears to be flat. In cosmology, flat means that parallel lines stay parallel forever. Euclidean geometry applies on cosmic scales. Measurements of the cosmic microwave background show the universe is flat to within measurement error. A flat universe that started from the Big Bang and has been expanding ever since is infinite in spatial extent. It was always infinite. Even at the Big Bang, it was infinitely large, though infinitely dense. This is hard to wrap your head around. How can something infinite expand? The answer is that distances between points increase, but the total size stays infinite. Infinity plus anything is still infinity. An infinite universe has mind-bending implications. Infinite galaxies, infinite stars, infinite planets, infinite Earth-like planets, infinite copies of you in an infinite universe. Every possible arrangement of matter exists somewhere. There are infinite versions of you reading this right now. Some are identical, some made different choices, some live in societies that develop differently. This isn't speculation. It's a mathematical consequence of infinity plus quantum mechanics. If the universe is infinite and matter is distributed randomly, then every possible configuration must exist somewhere. Cosmic structures, the universe's architecture. The universe isn't uniformly filled with galaxies. They're organized into structures. Galaxies cluster into galaxy groups, like our local group containing the Milky Way, Andromeda, and about 54 smaller galaxies. Galaxy groups. Cluster into chid galaxy clusters, like the Virgo cluster containing about 2,500 galaxies. Galaxy clusters. Cluster into superclusters, like the Laniakea supercluster containing about 100,000 galaxies including our local group. Superclusters. Form filaments and walls, vast structures hundreds of millions of light-years long, separated by enormous voids. The largest known structure is the Hercules Corona Borealis Great Wall, a galactic filament about 10 billion light-years long. It's so large it challenges cosmological models. Structures this big shouldn't exist, according to some theories. Between these structures are cosmic voids, vast empty regions containing very few galaxies. The largest known void, the Bootes void, is about 330 million light-years across. This cosmic web structure formed from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. It's the universe's architecture, shaped by dark matter and dark energy. The zoom out, perspectives on scale. Let's zoom out from Earth to the observable universe. Earth, 12,142 km diameter, 100x larger. Moon's orbit, 768,000 km diameter, 200 km larger. Sun, 1.4 million km diameter, 100x larger. Inner solar system, 150 million km. Earth's orbit, 60x larger. Solar system, 9 billion kilometers. Neptune's orbit, 10,000x larger. This Oort cloud, 100 trillion kilometer, 2 light-years, 2x larger. Nearest star system, 4.2 light-years. Alpha Centauri, 25,000x larger. Milky Way, 100,000 light-years, 25x larger. Local group, 10 million light-years, 10x larger. Virgo supercluster, 10 million light-years, 10x larger. Laniakea supercluster, 520 million light-years, 100x larger. Observable universe, 93 billion light-years. Each step increases the scale by factors of tens, hundreds, or thousands. The total scale from Earth to the observable universe is about 1027, a billion times larger. And if the universe is infinite, we could keep zooming out forever. More stars than grains of sand. The comparison, more stars than grains of sand, is often used, but let's actually check if it's true. Grains of sand on Earth. Average beach has about 10 or 18 grains of sand. Earth has about 10,000 beaches. Total, about 1022 grains of sand on all beaches. Stars in observable universe, 2x 10 RPM 23 stars. So yes, there are about 10 times more stars in the observable universe than grains of sand on all Earth's beaches. But what about all sand on Earth, including deserts and ocean floors? Estimates vary, but probably about 1024 grains total. So there are about 20 stars in the observable universe for every grain of sand on Earth. The universe is even more vast than the analogy suggests. Most will never be observed. Of the 2 billion trillion stars in the observable universe, how many have been observed by humans? In the Milky Way alone, there are 400 billion stars. We've cataloged maybe 1 billion of them. We've studied in detail maybe a few thousand. We can see with the naked eye about 5,000 on a dark night. That means we've directly observed less than 0.5% of stars in our own galaxy. The other 99.5% plus have never been seen by human eyes and probably never will be. And that's just our galaxy. There are 2 trillion other galaxies, most so distant we can barely resolve them. The vast majority of stars in the universe will never be observed by anyone, ever. This is humbling. The universe is so vast that most of it will remain forever unknown to us. We're like ants on a beach, able to explore only a tiny fraction of the grains of sand around us. But allures, the cosmic horizon, what we can never see. Due to the universe's expansion, there's a cosmic horizon beyond which we can never see, no matter how long we wait. Light from beyond this horizon is receding faster than light speed due to cosmic expansion. It will never reach us. As time passes, more and more of the universe crosses this horizon, disappearing from view forever. In the far future, as dark energy continues to accelerate the universe's expansion, the cosmic horizon will shrink. Distant galaxies will redshift into invisibility. Eventually, only our local group of gravitationally bound galaxies will remain visible. The rest of the universe will have receded beyond the horizon. Future civilizations, billions of years from now, will look at the sky and see only their local galaxy cluster. They'll have no evidence of the Big Bang, no cosmic microwave background, no distant galaxies. They might conclude they live in a small, static universe. We're fortunate to live in an era when we can still see the universe's history written in the sky. Conclusion: embrace the incomprehensible. The universe is bigger than your brain can comprehend. 93 billion light-years across, 2 trillion galaxies, 200 billion trillion stars, possibly infinite. You can write these numbers, you can do math with them, but you can't truly grasp them. Your intuition fails, your imagination falls short, and that's okay. The universe doesn't require your comprehension. It exists on scales far beyond human experience, governed by laws that produce structures of unimaginable size and complexity. We're infinitesimally small in this vast cosmos. Earth is a pale blue dot. The solar system is a speck. The Milky Way is one of trillions. And all of it, all 93 billion light-years, might be just an infinitesimal fraction of an infinite whole. This could be depressing. We're so small, so insignificant. But it's also liberating. We're part of something vast and magnificent. We're the universe's way of knowing itself, and that's pretty amazing. Reality is not what it seems. Welcome to the quantum realm, where reality breaks down, common sense fails, and the universe reveals its deepest strangeness. A realm where particles are waves, where observation changes reality, where things can be in two places at once, and where the future might affect the past. Quantum mechanics is the most successful scientific theory ever created. It's been tested to extraordinary precision and has never failed. It's the foundation of modern technology. Computers, smartphones, lasers, GPS, and medical imaging all depend on quantum mechanics. But it's also deeply weird. Even physicists who work with it daily admit they don't truly understand it. As Richard Feynman famously said, "I think I can safely say that nobody understands quantum mechanics." And here's the kicker. Quantum weirdness isn't confined to the microscopic world. It operates on cosmic scales, shaping the universe itself. Quantum fluctuations created galaxies. Quantum tunneling powers stars. Quantum effects determine the fate of black holes. The universe is quantum to its core. And that makes reality far stranger than we ever imagined. Wave-particle duality. Everything is both light is a wave. We know this because it diffracts, interferes, and has wavelength and frequency. Thomas Young proved it in 1801 with his double-slit experiment. Light is a particle. We know this because it comes in discrete packets, photons, with specific energies. Albert Einstein proved it in 1905, explaining the photoelectric effect. Both statements are true. Light is both wave and particle, depending on how you observe it. This is wave-particle duality, and it's one of the fundamental principles of quantum mechanics. But it gets weirder. Matter also exhibits wave-particle duality. Electrons, protons, atoms, even molecules show wave-like behavior. In 1999, researchers demonstrated interference patterns with molecules containing 60 carbon atoms, buckyballs. In 2019, they did it with molecules containing over 2,000 atoms. Where does wave-particle duality end? Does it apply to viruses, bacteria, humans? In principle, yes. Everything has a wavelength given by the de Broglie relation. L frar pointers hp. Wavelength equals Planck's constant divided by momentum. For large objects, the wavelength is so tiny it's unmeasurable. Your wavelength, as you sit reading this, is about 10 ordre 35 meters, far smaller than the Planck length, the smallest meaningful distance in physics. But it exists. The universe is made of waves, or particles, or both, depending on how you look. The double-slit experiment, reality's greatest mystery. The double-slit experiment is simple to describe but impossible to understand. It reveals the heart of quantum weirdness. Setup: Fire particles, photons or electrons, at a barrier with two slits. Behind the barrier is a detector screen. If particles go through one slit or the other, you'd expect two bands on the screen, one behind each slit. But that's not what happens. You get an interference pattern, multiple bands, characteristic of waves interfering with each other. Okay, so particles are waves, but then you try to observe which slit each particle goes through. You add detectors at the slits. Now the interference pattern disappears. You get two bands, as if the particles are particles, not waves. The act of observation changes the outcome. When you're not looking, particles behave like waves, going through both slits simultaneously and interfering with themselves. When you are looking, they behave like particles, going through one slit or the other. This has been tested countless times with increasing sophistication. The result is always the same. Observation matters. Reality changes depending on whether you're watching. What counts as observation? Does it require a conscious observer, or just any interaction that could reveal which path information? Physicists debate this. The measurement problem, what constitutes a measurement and why it causes wave function collapse, remains unsolved. Quantum entanglement, spooky action at a distance. Create two particles in a quantum entangled state, separate them by any distance, across the room, across the galaxy, across the universe. Measure one particle, and you instantly know the state of the other, no matter how far apart they are. This is quantum entanglement, and Einstein hated it. He called it spooky action at a distance and believed it proved quantum mechanics was incomplete. How could measuring one particle instantly affect another, light years away? That would require faster-than-light communication, violating relativity. But experiments have proven entanglement is real. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for experiments confirming quantum entanglement and ruling out local hidden variable theories. Entanglement doesn't allow faster-than-light communication. When you measure one particle, you get a random result. The other particle's measurement is correlated, but you can't control what result you get, so you can't send information. But the correlation is real and instantaneous. Measure one particle's spin as up, and the other is instantly down, even if it's on the other side of the universe. The particles remain connected in a way that transcends space. Entanglement might be the universe's most fundamental property. Some physicists believe space-time itself emerges from quantum entanglement. The universe might be a vast web of entangled particles, connected in ways we're only beginning to understand. The uncertainty principle. You can't know everything. Heisenberg's uncertainty principle states that you cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of measurement technology. It's a fundamental property of reality. Particles don't have definite position and momentum simultaneously. They exist in a superposition of possibilities, until measured. The uncertainty principle also applies to energy and time. A particle can borrow energy from the vacuum as long as it pays it back quickly enough. The more energy borrowed, the shorter the time allowed. This creates virtual particles, particle-antiparticle pairs that pop into existence from nothing, exist briefly, and annihilate. The vacuum isn't empty. It's seething with virtual particles, constantly being created and destroyed. These aren't just theoretical. Virtual particles have measurable effects. The Casimir effect, where two metal plates in a vacuum are pushed together by virtual particle pressure, has been experimentally verified. Virtual particles also contribute to the anomalous magnetic moment of the electron, calculated and measured to agree to 12 decimal places. The uncertainty principle means the universe is fundamentally fuzzy. There's a limit to how much you can know, not because of technological limitations, but because reality itself is indeterminate at the quantum level. Quantum tunneling, passing through walls. In classical physics, if a ball doesn't have enough energy to roll over a hill, it can't get to the other side. In quantum mechanics, it can tunnel through the hill. Quantum tunneling occurs when a particle passes through a barrier it classically shouldn't be able to cross. This happens because particles are waves, and waves can penetrate barriers. The probability of tunneling decreases exponentially with barrier thickness and height, so it's only significant for small particles and thin barriers. But it's real and measurable. The sun shines because of quantum tunneling. In the sun's core, protons must fuse to create helium, but protons repel each other electromagnetically. They need enormous energy to overcome this repulsion and get close enough for the strong nuclear force to bind them. The sun's core temperature provides some energy, but not enough. Classically, fusion shouldn't occur at solar temperatures, but quantum tunneling allows protons to tunnel through the electromagnetic barrier, enabling fusion at lower energies. Without quantum tunneling, the sun wouldn't shine. Stars wouldn't exist. The universe would be dark and lifeless. Tunneling also enables radioactive decay, scanning tunneling microscopes, and flash memory in your computer. It's a fundamental quantum process with cosmic implications. Hawking radiation, black holes. Evaporate. Black holes aren't perfectly black. They emit radiation due to quantum effects near the event horizon. This is Hawking radiation, predicted by Stephen Hawking in 1974. Here's how it works. Virtual particle pairs constantly pop into existence near the event horizon. Normally, they quickly annihilate, but if one particle falls into the black hole while the other escapes, the escaping particle becomes real radiation. From outside, it looks like the black hole is emitting particles. The energy for this comes from the black hole's mass, so the black hole slowly evaporates. For stellar mass black holes, Hawking radiation is negligible, far colder than the cosmic microwave background. But for tiny black holes, it's significant. A black hole with the mass of a mountain would evaporate in seconds, releasing energy equivalent to millions of nuclear bombs. Hawking radiation means black holes aren't eternal. Given enough time, an unimaginably long time, they'll evaporate completely. A solar mass black hole will take 10^67 years to evaporate. The supermassive black hole at the Milky Way center will take 100 years. But eventually, all black holes will evaporate, leaving only radiation. This is the black hole's ultimate fate, determined by quantum mechanics. Quantum fluctuations created the universe. The universe began as a quantum fluctuation. This sounds absurd, but it's the leading explanation for cosmic inflation and the Big Bang. In the first fraction of a second after the Big Bang, the universe underwent inflation, exponential expansion driven by a quantum field. Quantum fluctuations in this field created tiny density variations. These variations were stretched to cosmic scales by inflation. After inflation ended, gravity amplified these variations over billions of years, creating the cosmic web of galaxies and voids we see today. The cosmic microwave background shows these primordial fluctuations. The tiny temperature variations, about 1 part in 100,000, are the seeds of all cosmic structure. They originated as quantum fluctuations smaller than an atom, stretched to the size of the observable universe. Everything, galaxies, stars, planets, exists because of quantum fluctuations in the first 10⁻⁻⁵ seconds of the universe's history. The quantum realm created the cosmos. The measurement problem, Schrödinger's cat. Schrödinger's cat is a thought experiment illustrating the measurement problem in quantum mechanics. A cat is in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers, breaking the vial and killing the cat. Quantum mechanics says the atom is in a superposition of decayed and not decayed until measured. Therefore, the cat is in a superposition of alive and dead until you open the box and observe it. Only then does the wave function collapse, and the cat becomes definitely alive or dead. This seems absurd. Cats aren't in superpositions. They're either alive or dead whether you're looking or not. But quantum mechanics, taken literally, says otherwise. This is the measurement problem. What counts as a measurement? When does wave function collapse occur? Does it require a conscious observer? Copenhagen interpretation. Wave function collapse occurs upon measurement. What constitutes measurement is undefined. Many worlds. Interpretation. No collapse occurs. The universe splits into branches, one where the cat is alive and one where it's dead. Both exist in parallel. Objective collapse. Theories. Collapse occurs spontaneously when systems reach a certain size or complexity, independent of observation. Pilot wave theory. Particles have definite positions guided by a wave. No collapse needed. Physicists don't agree on which interpretation is correct. The measurement problem remains unsolved after nearly a century. Quantum foam, space-time at the smallest scales. At the Planck scale, 10 or 35 meters in 1043 seconds, space-time itself becomes quantum. It's no longer smooth but foamy, fluctuating wildly due to quantum uncertainty. At these scales, virtual black holes might constantly form and evaporate. Wormholes might connect distant points. The very fabric of spacetime might be in constant flux. We can't observe the Planck scale directly. It's far too small. But quantum gravity theories, like string theory and loop quantum gravity, attempt to describe it. If these theories are correct, spacetime is emergent. It arises from more fundamental quantum entities. Space and time aren't fundamental, but are collective properties of underlying quantum degrees of freedom. This would mean the universe is quantum all the way down. There's no classical foundation. It's quantum turtles all the way down. Conclusion. Embrace the weirdness. Quantum mechanics is weird. Particles are waves. Observation changes reality. Things can be in two places at once. Virtual particles pop in and out of existence. Black holes evaporate. The universe began as a quantum fluctuation. None of this makes intuitive sense. Our brains evolved to understand medium-sized objects moving at medium speeds, not atoms or galaxies, not quantum superpositions or cosmic inflation. But quantum mechanics works. It's been tested more rigorously than any other scientific theory. It's never failed. It's the foundation of modern technology and our understanding of the universe. The universe is quantum. Reality is probabilistic, not deterministic. Observation matters. Entanglement connects distant particles. Uncertainty is fundamental. This isn't a bug in our understanding. It's a feature of reality. The universe is stranger than we imagined, and quantum mechanics reveals that strangeness in all its glory. Welcome to the quantum universe. It's weird, it's wonderful, and it's the only reality we've got. Everything you see is history. Right now, as you read this, you're looking at the past. The light from these words took a tiny fraction of a second to travel from the screen to your eyes. By the time you see them, they're already history. Look out a window. The sunlight streaming through left the sun 8 minutes and 20 seconds ago. You're seeing the sun as it was 8 minutes in the past. If the sun exploded right now, you wouldn't know for 8 minutes. Look up at the night sky. Every star you see is a ghost, an image from the past. Some stars you see tonight died centuries ago, but their light is still traveling through space, only now reaching Earth. The universe has a speed limit. The speed of light, and this limit means we're forever looking backward in time. The farther we look, the further back we see. Telescopes aren't just instruments for seeing distant objects. They're time machines, showing us the universe as it was billions of years ago. Welcome to the cosmic light speed delay, where the present is always out of reach and everything is history. The speed of light, the universe's speed limit. Light travels at 299,792,458 meters per second in a vacuum. That's about 300,000 kilometers per second, or 186,000 miles per second. This seems incredibly fast. Light could circle Earth's equator 7.5 times in 1 second. It could travel from Earth to the Moon in 1.3 seconds. But on cosmic scales, light is slow, really slow. Space is so vast that even light takes years, centuries, or billions of years to cross it. Einstein's special relativity tells us that nothing can travel faster than light. This isn't just a speed limit for matter, it's a fundamental property of space-time. Light speed is the speed of causality. the maximum rate at which information can propagate through the universe. Why can't anything go faster? Because as you approach light speed, strange things happen. Time slows down, distances contract, your mass increases. At exactly light speed, time would stop, distances would shrink to zero, and your mass would become infinite. This is impossible for anything with mass. Only massless particles like photons can travel at light speed. Everything else must go slower. This speed limit creates the cosmic light speed delay. When you look at distant objects, you're not seeing them as they are now. You're seeing them as they were when the light left them. Seeing the sun. 8 minutes in the past. The sun is about 150 million kilometers, 93 million miles, from Earth. Light takes about 8 minutes and 20 seconds to cover this distance. This means you never see the sun as it is now. You always see it as it was 8 minutes and 20 seconds ago. If the sun suddenly vanished right now, Earth would continue orbiting normally for 8 minutes and 20 seconds. We'd still see the sun in the sky, still feel its warmth. Then, 8 minutes and 20 seconds later, the sun would disappear from the sky and Earth would fly off in a straight line, no longer held in orbit by the sun's gravity, which also propagates at light speed. This isn't just theoretical. Solar astronomers see solar flares 8 minutes after they occur. When a coronal mass ejection erupts from the sun, we don't know about it until 8 minutes later. This delay is crucial for space weather forecasting. The light speed delay also affects communication with spacecraft. Mars is between 4 and 24 light minutes from Earth, depending on orbital positions. Commands sent to Mars rovers take 4 to 24 minutes to arrive. Responses take another 4 to 24 minutes to return. You can't drive a Mars rover in real time. There's always a GPS delay. The nearest stars, years in the past. The nearest star system, Alpha Centauri, is 4.24 light-years away. The light you see from Alpha Centauri tonight left that star 4.24 years ago, in 2020, if you're reading this in 2025. Sirius, the brightest star in the night sky, is 8.6 light-years away. You see it as it was 8.6 years ago. Betelgeuse, the red supergiant in Orion, is about 640 light-years away. The light you see tonight left Betelgeuse in the year 1385, during the Middle Ages. Betelgeuse is nearing the end of its life. It could explode as a supernova any time in the next 100,000 years. But here's the thing. It might have already exploded. If it exploded 500 years ago, we won't know for another 140 years. When Betelgeuse does explode, or when we see it explode, it will be bright enough to see during the day, possibly as bright as the full moon. It will be visible for weeks or months, but we'll be seeing an explosion that occurred 640 years in the past. Every star in the night sky is a time capsule, showing us the universe as it was years, decades, or centuries ago. The Milky Way. Thousands of years in the past. Most stars visible to the naked eye are within a few hundred to a few thousand light years. The farthest naked eye star, V762 Cas, is about 16,000 light years away. When you see it, you're looking 16,000 years into the past, back to the last ice age. The Milky Way is about 100,000 light years across. Light from the far side of our galaxy takes 100,000 years to reach us. We see the distant parts of our galaxy as they were 100,000 years ago, when Homo sapiens was just beginning to migrate out of Africa. The center of the Milky Way is about 26,000 light years away. The supermassive black hole at the center, Sagittarius A, appears to us as it was 26,000 years ago. If something dramatic happened there today, we won't see it for 26,000 years. This creates a strange situation. Different parts of the galaxy exist in different times from our perspective. We see nearby stars as they were recently, distant stars as they were long ago. There's no universal now for the galaxy, only a patchwork of different pasts. Andromeda, 2.5 million years in the past. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light years away. The light you see from Andromeda tonight left that galaxy 2.5 million years ago, when our ancestors were Australopithecus, just beginning to use stone tools. Andromeda is approaching the Milky Way at about 110 kilometers per second. In about 4 to 5 billion years, the two galaxies will collide and merge. But we're seeing Andromeda as it was 2.5 million years ago. Its current position is different from where we see it. When astronomers calculate the future collision, they must account for this light speed delay. They're predicting the future based on observations of the past, extrapolating motion forward in time. Most galaxies we can see with amateur telescopes are millions of light years away. The Triangulum Galaxy, 3 million light years. The Sombrero Galaxy, 29 million light years. The Whirlpool Galaxy, 23 million light years. Each is a window into the past, showing us how these galaxies looked millions of years ago. Deep space, billions of years in the past. The Hubble Space Telescope's deep field images show galaxies billions of light years away. The Hubble Ultra Deep Field, a tiny patch of sky observed for 11 days, contains about 10,000 galaxies, most of them billions of light years distant. The farthest galaxy in that image, UDFJ 39546284, is about 13.2 billion light years away. We see it as it was then 13.2 billion years ago, just 600 million years after the Big Bang, when the universe was only 4% of its current age. That galaxy might not exist anymore. It's had 13.2 billion years to evolve, merge with other galaxies, or be torn apart. We're seeing its ancient past with no way to know its present. The James Webb Space Telescope, launched in 2021, can see even farther. It's designed to observe the first galaxies that formed, just 100–200 million years after the Big Bang. These galaxies are so distant that we're seeing them as they were over 13.5 billion years ago. When we look at these distant galaxies, we're not just seeing far away, we're seeing far back in time. We're observing the universe's history, watching galaxies form and evolve in the early cosmos. The cosmic microwave background, 13.8 billion years in the past. The farthest we can see is the cosmic microwave background, CMB, radiation from 380,000 years after the Big Bang, when the universe first became transparent. Before this time, the universe was opaque, a hot, dense plasma that absorbed all light. When the universe cooled enough for atoms to form, light could finally travel freely. This first light has been traveling through space for 13.8 billion years, and we detect it today as the CMB. The CMB is the oldest light in the universe. It's a baby picture of the cosmos, showing us what the universe looked like when it was only 380,000 years old. We can't see farther back than the CMB with light. The universe before 380,000 years was opaque. To probe earlier times, we need other methods: gravitational waves, neutrinos, or hypothetical particles that could escape the early universe. But the CMB is remarkable enough. When you look at a map of the CMB, you're seeing the universe as it was 13.8 billion years ago. You're looking at the seeds of all cosmic structure, the tiny density fluctuations that would grow into galaxies, clusters, and the cosmic web. Most stars we see are already dead. Stars have finite lifetimes. Massive stars live only a few million years. Medium stars like the Sun live about 10 billion years. Small red dwarfs can live trillions of years. Many of the stars we see in the night sky are massive and distant. They've been shining for millions of years, and their light has been traveling for hundreds or thousands of years to reach us. Some of these stars have already died. They exploded as supernovae, collapsed into black holes, or shed their outer layers to become white dwarfs. But we don't know it yet. Their light is still traveling through space, and we still see them shining. Betelgeuse might already be gone. Eta Carinae, a massive star 7,500 light-years away, might have exploded 7,000 years ago, and we won't see it for another 500 years. When you look at the night sky, you're seeing a mixture of living and dead stars. Some are still shining. Some are already gone. You can't tell which is which. You can only see the past. Simultaneity is relative. Einstein's relativity tells us there's no universal now. Events that are simultaneous for one observer may not be simultaneous for another. Imagine two events happening on opposite sides of the galaxy, 100,000 light-years apart. For an observer at rest relative to the galaxy, they might occur at the same time. But for an observer moving at high speed, one event occurs before the other. This means now is relative. What's happening right now on a distant planet depends on your motion. Change your velocity, and you change which distant events are happening now. This has profound implications. The universe doesn't have a universal present moment. There's no cosmic now that applies everywhere. Time is local, personal, and relative. For distant objects, the concept of now becomes almost meaningless. When we say Andromeda is 2.5 million light-years away, we mean Andromeda was 2.5 million light-years away when the light we're seeing left it. Where is Andromeda now? The question doesn't have a definite answer. It depends on your reference frame. The observable universe's edge, the cosmic horizon. The observable universe has an edge, not an edge in space, but an edge in time. It's the cosmic horizon beyond which we cannot see. Light from beyond this horizon hasn't had time to reach us yet. The universe is 13.8 billion years old, so we can only see objects whose light has had 13.8 billion years to travel. Accounting for cosmic expansion, this corresponds to objects now about 46.5 billion light-years away. Beyond this horizon is more universe, possibly infinite universe, that we can never observe. Not because it's too far away, but because its light hasn't reached us yet, and due to accelerating cosmic expansion, never will. This creates a strange situation. There are galaxies that exist, but that we can never see. There are events happening that we can never observe. There's a whole universe beyond our horizon, forever hidden from view. As time passes, the horizon expands. We can see farther and farther back in time. But due to cosmic acceleration, the horizon is also receding in another sense. Distant galaxies are crossing it, disappearing from view forever. Future archaeologists will see a different universe. In the far future, billions of years from now, the universe will look very different. Dark energy is accelerating cosmic expansion. Distant galaxies are receding faster and faster. Eventually, they'll recede so fast that their light can never reach us. They'll cross the cosmic horizon and disappear. In about 100 billion years, all galaxies outside our local group will have receded beyond the horizon. Future astronomers will look at the sky and see only their local galaxy cluster. The rest of the universe will be invisible. The cosmic microwave background will also fade. It's already redshifted to microwave wavelengths. As the universe expands, it will redshift further, to radio waves, then to wavelengths so long they're undetectable. Future civilizations will have no evidence of the Big Bang, no distant galaxies, no cosmic microwave background, no redshift. They might conclude they live in a small, static universe containing only their local cluster. We're fortunate to live in an era when we can still see the universe's history. We can observe distant galaxies, measure cosmic expansion, and detect the CMB. Future civilizations won't have this privilege. Conclusion: embrace the delay. We're living in the past. Everything we see is history. The sun, 8 minutes ago. The stars, years or centuries ago. Distant galaxies, billions of years ago. There's no way around this. Light has a finite speed, and space is vast. The cosmic light speed delay is fundamental to how we experience the universe. But this delay is also a gift. It allows us to see the universe's history. Telescopes are time machines, showing us how galaxies formed, how stars evolved, how the cosmos changed over billions of years. When you look at the night sky, you're not just seeing space, you're seeing time. You're looking at a patchwork of different eras, from the recent past, nearby stars, to the ancient past, distant galaxies, to the very beginning, the cosmic microwave background. We can never see the present universe. We can only see its past. But that past is magnificent, revealing the story of cosmic evolution written in light across billions of years. Welcome to the universe's history book. It's written in starlight, and it's the most amazing story ever told. What we don't know. Science has revealed incredible truths about the universe. We know how stars form, how galaxies evolve, how the universe began. We've measured the age of the cosmos, mapped its large-scale structure, and detected gravitational waves from colliding black holes. But for all we know, there's far more we don't know. The universe is filled with mysteries, fundamental questions that remain unanswered despite decades or centuries of research. Some of these mysteries might be solved soon, others might take generations, and some might be forever beyond our understanding, limited by the laws of physics or the nature of reality itself. This chapter is about what we don't know, about the questions that keep cosmologists awake at night, about the mysteries that define the frontier of human knowledge. Welcome to the edge of understanding, where known meets unknown. Mystery 1. What is dark matter? Dark matter makes up about 27% of the universe, more than 5 times as much as ordinary matter. We know it exists because of its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than we can see. The universe's large-scale structure requires more gravity than visible matter provides. But we don't know what dark matter is. We've never directly detected a dark matter particle. Leading candidates: WIMPs, weakly interacting massive particles. Hypothetical particles that interact only through gravity and the weak nuclear force. Experiments like LEX, Xenon, and Super CDMS have searched for WIMPs for decades. So far, nothing. Axions, hypothetical ultralight particles proposed to solve a problem in quantum chromodynamics. Experiments like ADMX are searching for them. So far, nothing definitive. Primordial black holes. Black holes formed in the early universe from density fluctuations. They could have any mass and would be invisible unless actively feeding. Some observations constrain their abundance, but they remain possible. Sterile neutrinos. Hypothetical particles that don't interact via any force except gravity. Hard to detect, but some anomalies in neutrino experiments might hint at them. Modified gravity. Maybe dark matter doesn't exist. Maybe our understanding of gravity is wrong. Theories like Amond, modified Newtonian dynamics, attempt to explain galactic rotation without dark matter. But they struggle to explain other observations like galaxy clusters and the cosmic microwave background. Despite decades of searching and billions of dollars spent on experiments, we still don't know what dark matter is. It's one of the biggest unsolved problems in physics. Mystery 2. What is dark energy? If dark matter is mysterious, dark energy is even more so. It makes up about 68% of the universe, more than twice as much as dark matter, and we have even less idea what it is. Dark energy is the name we give to whatever is causing the universe's expansion to accelerate. In the 1990s, observations of distant supernovae revealed that the universe's expansion is speeding up, not slowing down as expected. This was shocking. Gravity should slow expansion. Something must be pushing space apart, working against gravity. We call it dark energy, but that's just a name for our ignorance. Possible explanations. Cosmological constant. Einstein's equations allow for a constant energy density in empty space. This vacuum energy would cause accelerated expansion. The problem, when physicists calculate how much vacuum energy there should be, they get a number 10^-120 pound times larger than observed. This is the worst prediction in the history of physics. Quintessence. A dynamic field that changes over time, unlike the cosmological constant, which is constant. This could explain why dark energy has the value it does now, but it requires introducing new physics. Modified gravity. Maybe dark energy doesn't exist. Maybe general relativity breaks down on cosmic scales. Theories like FR gravity attempt to explain cosmic acceleration without dark energy, but they face challenges matching observations. Anthropic principle. Maybe the cosmological constant has the value it does because if it were different, we wouldn't exist to observe it. This is philosophically unsatisfying, but might be the answer. Dark energy will determine the universe's ultimate fate. If it's constant, the universe will expand forever, eventually tearing apart all structures in a big rip. If it weakens, expansion might slow or even reverse. We don't know which will happen because we don't know what dark energy is. Mystery 3. What happened before the Big Bang? The universe began 13.8 billion years ago in the Big Bang. But what happened before that? The standard answer is nothing. Time itself began at the Big Bang. Asking what happened before is like asking what's north of the North Pole. The question doesn't make sense. But some physicists aren't satisfied with this answer. Several theories propose what might have come before. Cyclic universe. The universe goes through endless cycles of big bangs and big crunches. Our Big Bang was the end of a previous universe's big crunch. This avoids the question of ultimate origins, but raises others. What started the cycles? Why do they continue? Multiverse. Our universe is one of many, perhaps infinitely many, in a larger multiverse. The Big Bang was a local event in this larger structure, but this pushes the question back. Where did the multiverse come from? Quantum fluctuation. The universe began as a quantum fluctuation from nothing. Quantum mechanics allows energy to be borrowed briefly. Perhaps the universe borrowed energy from nothing and never paid it back. But what is nothing, and what laws governed it? Eternal inflation. Inflation, the exponential expansion in the universe's first fraction of a second, might be eternal. Our universe is a bubble where inflation ended, but inflation continues elsewhere, creating infinite universes. But what started inflation? We might never know what happened before the Big Bang. The Big Bang itself might have erased all evidence of what came before, or the question might be meaningless. Time might truly have begun at the Big Bang. Mystery 4. Why is there something rather than nothing? This is perhaps the deepest question in all of science and philosophy. Why does the universe exist? The Big Bang explains how the universe evolved from a hot, dense state, but it doesn't explain why there was a hot, dense state to begin with. Why is there something rather than nothing? A related mystery. Why is there more matter than antimatter? In the early universe, matter and antimatter should have been created in equal amounts. They should have annihilated each other, leaving only radiation. But somehow, there was a tiny excess of matter. About one extra matter particle for every billion matter-antimatter pairs. This excess became everything we see. Why? We don't know. This is called the baryon asymmetry problem. Several mechanisms have been proposed: CP violation, leptogenesis, electroweak baryogenesis, but none fully explains the observed asymmetry. The existence of the universe might be the ultimate mystery, one that science can never fully answer, because it requires explaining why there are laws of physics at all. Mystery 5. Are we alone? The Fermi paradox. The universe is vast, 200 billion trillion stars, probably trillions of planets, many in the habitable zones of their stars. Life arose on Earth. Why not elsewhere? The Drake equation attempts to estimate the number of communicating civilizations in the galaxy. N fought Q XFP XNEXFL X Phi XFCXL, where R equals star formation rate, FP linear fraction of stars with planets, NEAT number of habitable planets per star with planets, FL Baudrillard fraction where life arises, Phi Stadler fraction where intelligent life evolves, FC Adler fraction that developed detectable technology, ELR length of time, civilizations are detectable. Depending on the values you plug in, you get anywhere from we're alone to millions of civilizations in our galaxy. But we've detected no evidence of alien civilizations, no radio signals, no megastructures, no visits. This is the Fermi paradox. If aliens exist, where are they? Possible solutions. We're first. Maybe we're among the first intelligent civilizations in the galaxy. Someone has to be first. They're rare. Maybe one or more terms in the Drake equation is very small. Maybe life is rare, or intelligence is rare, or technological civilizations are rare. The Great Filter. Maybe there's a barrier that prevents civilizations from becoming spacefaring. Maybe it's behind us, hard to evolve intelligence, or ahead of us, civilizations self-destruct. They're hiding. Maybe advanced civilizations deliberately avoid contact. The zoo hypothesis suggests we're being observed but not contacted. They're here. Maybe aliens have visited Earth. Most scientists reject this due to lack of evidence, but it remains a possibility. We're not listening right. Maybe aliens use communication methods we haven't thought of. Or maybe they're so advanced we can't recognize their technology. The Fermi paradox remains unsolved. We don't know if we're alone or if the galaxy is teeming with life. Either answer is profound. Mystery 6. What's inside black holes? At the center of a black hole, general relativity predicts a singularity, a point of infinite density where the laws of physics break down. But infinity is usually a sign that a theory is incomplete. Most physicists believe singularities don't actually exist, that quantum mechanics prevents true infinities. But we don't have a theory of quantum gravity to describe what really happens. String theory, loop quantum gravity, and other approaches offer possibilities, but none are confirmed. The information paradox. When matter falls into a black hole, what happens to the information it contains? Quantum mechanics says information can't be destroyed, but general relativity says it's lost behind the event horizon. When the black hole evaporates via Hawking radiation, where does the information go? Stephen Hawking proposed that information is destroyed, violating quantum mechanics. Others proposed it's preserved in Hawking radiation, but encoded in ways we don't understand. The firewall paradox suggests the event horizon might be a wall of high-energy particles that destroys infalling matter. We don't know which is correct. The information paradox remains one of the deepest problems in theoretical physics. Mystery 7. Why these laws of physics? The laws of physics have specific values: the strength of gravity, the mass of the electron, the speed of light. But why these values? If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars wouldn't form. If the strong nuclear force were slightly different, atoms couldn't exist. If the cosmological constant were much larger, the universe would have expanded too fast for galaxies to form. The universe appears fine-tuned for life. Change almost any constant by a small amount, and life becomes impossible. Possible explanations. Anthropic principle. We observe these values because if they were different, we wouldn't exist to observe them. This is true but unsatisfying. It doesn't explain why the values are what they are. Multiverse. If there are infinite universes with different physical constants, some will have values compatible with life. We exist in one of those. This explains fine-tuning but is untestable. Design. Some argue fine-tuning implies a designer. This is a philosophical or religious position, not a scientific one. Deeper. Theory. Maybe the constants aren't arbitrary. Maybe a deeper theory explains why they have the values they do. String theory attempts this, but hasn't succeeded yet. We don't know why the laws of physics are what they are. It might be the deepest mystery of all. Mystery 8. The measurement problem in quantum mechanics. Quantum mechanics is the most successful theory in physics, but we don't understand what it means. The measurement problem. Quantum systems exist in superpositions until measured. Measurement causes wave function collapse, forcing the system into a definite state. But what counts as measurement? When does collapse occur? Why does it occur? Interpretations. Copenhagen. Collapse occurs upon measurement. What constitutes measurement is undefined. This is the standard. Interpretation, but philosophically unsatisfying. Many worlds. No collapse. The universe splits into branches for each possible outcome. All outcomes occur in parallel universes. This is elegant, but implies infinite parallel universes, or pilot wave. Particles have definite positions guided by a wave. No collapse needed, but this requires non-local hidden variables. Objective collapse. Collapse occurs spontaneously when systems reach a certain size. This is testable but not yet confirmed. After nearly a century, physicists still don't agree on what quantum mechanics means. The measurement problem remains unsolved. Mystery 9. Cosmic magnetic fields. The universe is filled with magnetic fields. Galaxies have them. Galaxy clusters have them. Even the voids between galaxies have weak magnetic fields. Where did these fields come from? How did they form? How are they maintained? We don't know. Magnetic fields should decay over time, yet they persist. Some process must be generating or amplifying them, but we don't know what. Theories include primordial fields from the early universe, dynamo processes in galaxies, shocks and turbulence in galaxy clusters, exotic physics in the early universe. Cosmic magnetic fields affect star formation, cosmic ray propagation, and galaxy evolution. Understanding them is crucial for understanding the universe, but they remain mysterious. Mystery 10. The Hubble tension. The Hubble constant measures how fast the universe is expanding. It should have a single value, but different measurement methods give different results. Measurements using the cosmic microwave background give about 67 kilometers as MPC. Measurements using distant supernovae give about 73 kilometers MPC. The difference is statistically significant, too large to be measurement error. This is the Hubble tension. Either one measurement is wrong, but we don't know which or why, or our cosmological model is incomplete. Possible explanations: unknown systematic errors in measurements, dark energy evolves over time, unknown physics in the early universe. Our cosmological model is wrong. The Hubble tension might be the first crack in the standard cosmological model, or it might be a measurement issue. We don't know yet. Conclusion. The known unknown. These mysteries aren't failures of science. They're the frontier. They're where our knowledge ends and the unknown begins. Some will be solved in our lifetimes, others might take centuries, and some might be forever beyond our reach, limited by the laws of physics or the nature of reality. But that's okay. Science isn't about knowing everything. It's about asking questions, testing ideas, and expanding the boundaries of knowledge. The universe is full of mysteries. That's what makes it fascinating. That's what drives us to explore, to question, to seek understanding. We don't know what dark matter is. We don't know what dark energy is. We don't know what happened before the Big Bang. We don't know if we're alone. We don't know what's inside black holes, but we're working on it. And that's the most human thing we do, facing the unknown and trying to understand it. The mysteries of the universe aren't obstacles. They're invitations. Invitations to explore, to discover, to push the boundaries of human knowledge, and that's the greatest adventure of all. Nothing lasts forever. Everything ends. Stars die, galaxies fade, even black holes evaporate. The universe itself has a finite future, not in time, but in usable energy, in complexity, in the possibility of life and structure. This chapter is about the future, the deep future, stretching trillions upon trillions of years into the cosmos. It's about the ultimate fate of stars, galaxies, and the universe itself. It's about the heat death of the cosmos, the evaporation of black holes, and the final state of reality. It's a story of endings, but also of incredible timescales that dwarf human history, like human history dwarfs a single heartbeat. Welcome to the far future, where even eternity comes to an end. Near future, the next few billion years. Let's start with timescales we can almost comprehend. Billions of years. 1 billion years from now. The sun is gradually brightening as it ages. In about 1 billion years, it will be about 10% brighter than today. This doesn't sound like much, but it's enough to evaporate Earth's oceans. The greenhouse effect will run away, turning Earth into a Venus-like hothouse. Life on Earth's surface will end. Billion years from now, the Milky Way and Andromeda galaxies collide. This sounds catastrophic, but galaxies are mostly empty space. Stars will pass by each other without colliding. The solar system might be flung to a different part of the merged galaxy or even ejected entirely. But Earth, if it still exists, will likely survive the collision. The merged galaxy will be an elliptical galaxy, nicknamed Milkomeda by astronomers. It will contain about 1 trillion stars, all the stars from both galaxies combined. Billion years from now, the Sun exhausts its hydrogen fuel and begins dying. It expands into a red giant, growing to about 250 times its current diameter. It will engulf Mercury and Venus. Earth might be engulfed too, or it might survive in a wider orbit. The Sun loses mass as it expands, weakening its gravity. Either way, Earth will be uninhabitable, a charred cinder orbiting a dying star. 7 billion years from now. The Sun sheds its outer layers in a planetary nebula, leaving behind a white dwarf, a dense Earth-sized remnant about half the Sun's current mass. This white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark cinder. If humanity still exists, we'll have long since left Earth, perhaps colonizing other star systems or even other galaxies. The Stelliferous Era, the last stars, 100 trillion years. We live in the Stelliferous Era, the age of stars. Stars are forming, shining and dying. The universe is bright and active, but star formation requires gas. As stars form, they convert gas into stars and stellar remnants. Eventually, the gas runs out. 100 trillion years from now, the last stars form. After this, no more gas remains to create new stars. The era of star formation ends. The universe will still contain stars, mostly small red dwarfs which can live for trillions of years, but no new stars will form. The universe has peaked and is beginning its long decline. 20 trillion years from now. The last red dwarfs burn out. The last stars die. The Stelliferous Era ends. After this, the universe contains only stellar remnants, white dwarfs, dead cores of sun-like stars, neutron stars, dead cores of massive stars, black holes from the most massive stars, brown dwarfs, failed stars that never ignited, planets now rogue, their stars long dead. The universe is dark. Occasional collisions between remnants might create brief flashes of light, but mostly, the cosmos is cold and dark. The Degenerate Era, dead stars, 1040 years. For an almost incomprehensible length of time, 1040 years, 1 trillion years, the universe exists in the Degenerate Era. It's called degenerate because it's dominated by degenerate matter, matter supported by quantum degeneracy pressure rather than thermal pressure. White dwarfs and neutron stars are made of degenerate matter. During this era, not much happens. The universe is cold and dark. Stellar remnants slowly cool. Occasionally, 2 white dwarfs collide, briefly creating a supernova. Occasionally, a brown dwarf captures a planet, creating a brief flash of heat. Galaxies slowly evaporate. Stars are ejected through gravitational interactions, wandering alone through intergalactic space. Galaxy clusters disperse. If protons are stable, and we don't know if they are, this era lasts essentially forever. White dwarfs and neutron stars would remain, cooling toward absolute zero, but never quite reaching it. But if protons decay, proton decay, the dissolution of matter. The standard model of particle physics says protons are stable, they last forever. But some theories beyond the standard model predict protons decay with a half-life of about 10^34 to 1040 years. We've never observed proton decay. Experiments have set lower limits on the proton's lifetime, at least 1034 years. But we don't know if protons are truly stable. If protons decay, then around 10^40 years, white dwarfs and neutron stars begin to evaporate. Protons decay into lighter particles, positrons, neutrinos, photons. The stellar remnants slowly dissolve. By 10^43 years, all protons have decayed. Matter as we know it no longer exists. The universe contains only black holes, electrons and positrons, neutrinos, photons. This is the end of the degenerate era and the beginning of the black hole era. The black hole era, Hawking radiation, 10 was 100 years. Black holes are the longest-lasting structures in the universe, but even they don't last forever. Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly evaporate. The evaporation rate is inversely proportional to the black hole's mass. Small black holes evaporate quickly. Large black holes evaporate slowly. A solar mass black hole will evaporate in about 10^67 years. The supermassive black hole at the Milky Way's center, 4 million solar masses, will evaporate in about 10^98 years. The largest known black holes, tens of billions of solar masses, will evaporate in about 10^100 years. During the black hole era, black holes are the only significant structures. They slowly evaporate, releasing Hawking radiation. As they shrink, they evaporate faster. In their final moments, they explode in a burst of radiation. By 10^100 years, even the largest black holes have evaporated. Nothing remains but radiation. The dark era, heat death, beyond 1000 years. After 1000 years, the universe enters its final state, the dark era. All black holes have evaporated. All structure has dissolved. The universe contains only photons stretched to enormous wavelengths by cosmic expansion, neutrinos, electrons and positrons, if they're stable, maybe some exotic particles. The temperature approaches absolute zero. Entropy approaches maximum. This is the heat death of the universe, a state of maximum disorder where no energy is available to do work. Nothing happens. Nothing can happen. The universe is dead. This state lasts forever. Time continues, but nothing changes. The universe has reached its final equilibrium. Or has it? Neutron, alternative fates, big rip, big crunch, big bounce. The heat death scenario assumes dark energy remains constant, but we don't know if that's true. Dark energy might change over time, leading to different fates. Big rip. If dark energy strengthens over time, cosmic expansion accelerates faster and faster. Eventually, expansion becomes so rapid that it tears apart galaxies, then solar systems, then planets, then atoms. In the final moments, space-time itself is torn apart. The universe ends not in cold darkness, but in violent disintegration. This could happen in as little as 20-50 billion years if dark energy is phantom energy that increases over time. Big crunch. If dark energy weakens or reverses, cosmic expansion could slow, stop, and reverse. The universe would begin contracting, galaxies would collide, the cosmic microwave background would heat up. Eventually, the universe would collapse back into a hot, dense state, a reverse Big Bang. This could lead to a big bounce. The universe rebounds from the crunch, creating a new Big Bang. The universe might be cyclical, going through endless cycles of expansion and contraction. Vacuum decay. Our universe might be in a false vacuum, a metastable state that could decay to a lower energy state. If this happens, a bubble of true vacuum would form and expand at light speed, destroying everything in its path. The laws of physics inside the bubble would be different. Atoms might not be stable. The universe as we know it would end. This could happen at any time. We'd have no warning. The bubble would arrive at light speed. But it's probably very unlikely. Or it would have happened already. Life in the far future. Could life survive in the far future? Around white dwarfs, trillions of years. White dwarfs remain hot for trillions of years. Civilizations could build Dyson spheres around them, capturing their heat. Life could continue long after normal stars die. Around black holes, 1067 years. Black holes emit Hawking radiation. Advanced civilizations might extract energy from this radiation or from matter falling into black holes. Life could persist as long as black holes exist. In the dark era, beyond 100 years. Once black holes evaporate, no energy sources remain. Life as we know it becomes impossible. But maybe life could adapt. Maybe consciousness could exist as patterns in quantum fields, requiring almost no energy. Maybe civilizations could enter a state of hibernation, thinking one thought every trillion years. Or maybe life ends when the stars die. We don't know. The ultimate question. Will the universe end? The heat death scenario suggests the universe continues forever, just in a dead, unchanging state. Time goes on, but nothing happens. But maybe the universe truly ends. Maybe vacuum decay destroys everything. Maybe quantum fluctuations eventually create a new Big Bang. Maybe the universe is cyclic and heat death is just a phase before rebirth. We don't know. Physics at these timescales is uncertain. We're extrapolating far beyond what we can test. The universe's ultimate fate remains one of the deepest mysteries in cosmology. Perspective. The cosmic calendar. Let's put these timescales in perspective using a cosmic calendar where the Big Bang occurred on January 1st and today is December 31st at midnight. On this scale, first stars form, January 13th, Milky Way forms, February 15th, solar system forms, September 2nd, life on Earth begins, September 21st, dinosaurs, December 26th, humans, December 31st, 11:58 p.m., recorded history, December 31st, 11:59 p.m. Now extend the calendar to include the far future. Sun dies 1.5 years from now. Last stars form. 2,500 years from now, last stars die. 3,000 years from now, proton decay. 250 million years from now, last black holes evaporate. 2.5 billion years from now, human civilization exists for the last 2 seconds of the first year. The universe continues for billions of years after. We live in the universe's infancy. The vast majority of cosmic time lies ahead. Conclusion. Embrace the temporary. Everything ends. The sun will die. The stars will fade. The universe will grow cold and dark. This could be depressing. We're temporary. Our civilization, our species, our planet, our star, our galaxy, all temporary. In the far future, it will be as if we never existed. But there's another way to look at it. We're incredibly fortunate to exist now in the stelliferous era when the universe is bright and active. We live in the universe's golden age when stars shine and life is possible. Billions of years from now, the universe will be dark and dead. But right now, it's alive. Right now, stars are forming, galaxies are colliding, planets are orbiting. Right now, we're here to witness it. The universe's temporary nature makes it precious. We have a limited time, cosmically speaking, to explore, to understand, to appreciate the cosmos. So look up at the stars, marvel at the galaxies, wonder at the mysteries. We're living in the universe's brief moment of glory, and we're fortunate enough to be aware of it. The future is long and dark, but the present is bright and full of wonder. And that's something worth celebrating.